I won't go too broadly into the proposal, but I'll quote one section of it. There is a significant underrepresentation of individuals of Black heritage in senior academic positions. Recipients of UKRI research funds and applicants to UKRI fellowship schemes are less than 1%. This trend clearly starts at PhD level, with only 1.2% of UKRI funding going to PhD students that are Black between 2016 and 2019. These numbers are stark and speak clearly to the broken pipeline, which inhibits recruitment and retention of Black students in academics. To improve the representation of Black engineering researchers across different career stages in academia, it is essential to leverage the excellence that already exists in the UK by increasing the visibility of these individuals. Such increased representation will benefit science, the academy, and society, helping the UK solidify its position on the global stage of science and technology. So, here we are, with the support of Imperial's Faculty of Engineering, hosting an event that will inspire, hopefully, the next generation of Black engineers and encourage the current generation to keep moving forward, to keep excelling in their field, to attend events like these, where we encourage multidisciplinary research, collaboration, mentorship, and support within the Black engineering research community so that we can fill the holes in the leaky pipeline of Black academia. We've got talks from a group of PhD researchers, academics, industry leaders, and experts in their fields. Speakers, don't forget that you're being timed. I will wave my flashcards at you when you have a minute left and when your time is over. And there will be time after each speaker speaks for questions and answer. There will also be short breaks in between each session, which I'll announce before our final talk by Professor West, who our scholarship scheme is named after. So get comfortable, get listening, and get ready to engage in great engineering research. Also, don't forget this is a safe space for us all. And afterwards, we have drinks, food, networking, music that you all hopefully submitted to. So it's going to be a vibe. Stay afterwards, have a great time. Don't forget as well, this event is being streamed, is being recorded, and photography is taking place as well. Okay, so our first session is our What is Engineering session, and our first speaker will be Samuel George White, our MRes student.
Wow. Okay. No, I'll keep it light. Nice to see everybody. Yeah, as Kemi said, my name's Samuel George White. Gosh, you know when your voice starts fluctuating, but anyway, we move. No, so I'll keep it light. Everyone else will talk about the research they're doing. So what is an engineering PhD? For a lot of people, especially myself, I didn't know, especially in secondary school, even while doing my undergrad. So essentially, typically, after you've done your master's, you can do a full-time PhD. That is about 3 or 4 years. So that's research on top of your master's degree. Then if you want, you can also do it as a 50% course, which takes a bit longer, but each to their own. The objective of a PhD is to build on all the knowledge you would have learned from primary school, secondary school, undergrad, your undergrad degree. If you do a master's, you get to build on that and kind of look into a focused research area. So you kind of get to, for the first time, pick your own question which you want to answer, which you want to research. I have a mechanical engineering background, but my PhD is in neuroscience and artificial intelligence. That's what I'm really interested in. I didn't get the chance to study that until basically after my master's and into a PhD. So that's kind of the idea of a PhD. You get to do focused research that you didn't get to earlier on in your education journey. Typically, as you're part of a research group, so you, unlike your undergrad where it would just be one lecturer in front of you just speaking at you, you're most likely going to be in a bit of a tight-knit group. It's called a research group, and that research group would have an advisor. You can have weekly or fortnightly catch-ups with your advisor, let him know how you're doing. Then also, you get to meet with a research group probably weekly, and there's a lot of cross-collaboration within your group. So if someone's doing something that you're interested in or is related to what you're researching in, that's how collaborations come about. You can end up doing joint papers, things like that. Like I said, the objective Am I good? Yeah.
Yeah.
Awesome. Like I said, the objective is to publish at the end of your PhD. That would come with, essentially, throughout the 3 years, your goal is to write a thesis. At the end of that, in the UK, typically, your thesis would go through a viva, which is my time up?
No,
Okay,
sorry.
wonderful. You go through a viva, which is essentially an examination of your thesis, the work you've done. It kind of gets judged, you ask questions on it, if it's essentially quality enough to be published. And yeah, that's a viva. It's less scary than it is, but if you kind of have been researching something that's quite novel, you'll most likely publish. Don't come see me if there's any issues, because I can't be held responsible. Okay, 1 minute. Yeah, briefly about my journey, actually. My year 13 was a shambles, I'll be completely honest. I actually had set my mind to come to Imperial to do my undergrad here. Year 13 hit me, it's crazy. So I ended up going to University of Southampton, doing my bachelor's in mechanical engineering, then coming here, doing my MRes, and then the PhD. And that's kind of just to let people know, like, even if you feel like it's a long way off, or even in your undergrad, if it feels like it's proper difficult, if you keep that kind of passion and that tenacity, if there's definitely something in you that you want to research or you want to kind of, bring to the world, however you want to call it, a PhD is definitely still possible. It does take a lot of hard work, a lot of discipline, and it's a lot more independent than what you're used to. But when you're around like a good community, like, you're good. So PhD is definitely a good opportunity. Yeah.
Just going to open up the floor if anyone's got any questions for Samuel before we move on to our next speaker. Yes, there's a lady at the back right there. Hi.
I was going to ask, you see your background was in mechanical engineering. Did you feel like underqualified when you went to study neuroscience at PhD level? Because you didn't really know about that.
Yeah, not gonna lie. Yeah. Essentially, but it's like a journey, to be honest. So I did my undergrad in mechanical. Doing that, I kind of liked a lot of the robotics and programming modules a lot more than I did maths and things like that. So that kind of pushed me to want to change. That's how I got into AI programming. Then once I was in AI programming and interested in that, doing some projects on that, I realized, the most interesting part is, neuroscience. That's kind of what I like. So even though it was like kind of daunting, because it was a gradual process, it didn't hit me like that. And even before I actually officially did the PhD, I did my MRes in bioengineering, which got me more familiar with the neuroscience. So the background that I didn't have, I still had time to kind of build it up before I entered the PhD. So hopefully that answers your question.
Yeah.
Thank you. Are there any other questions?
I don't know if it's been brought up earlier, but I don't know if you want to say something about the money and the funding that goes along with doing a PhD.
We're going to get to that.
Straight to the point. Love that. So for the MRes, actually, so that's still similar to an undergraduate degree. If you're a UK or home student, there's student finance available that can cover it. For the PhD, that would be self-funded, obviously as part of the James West Scholarship. I was 1 out of 3 that made it. I'm going to write that down. That actually covers the tuition fees for the whole PhD course, and also you're given a stipend, which is, there's a correct term for it. I think it's roughly that. No, let me not get it wrong. But it comes with a stipend, which this kind of helps you with your living costs throughout the time of your PhD, which is also a good benefit. So yeah.
All right, great, thank you. Oh, sorry, we've got one more question at the back here. I'll get my steps in today, thank you.
So what's the next step for you personally after leaving Imperial?
After the PhD? Wow.
Come a lecturer.
Stretching me. Now, what I do want to get into first, or two things actually. Firstly is to kind of like this, but just kind of build up a society of people that want to learn more about science, want to learn more about STEM subjects that don't really know much about it. For example, like I said, if I knew about programming, I didn't get to do it at GCSE or A level. I only found out about it the last few years of my undergrad. If I knew about it from then, I would have picked it and I would have been kind of doing what I wanted to do a lot earlier. So kind of just a community to raise awareness of what's actually out there, the different research avenues. After, a lot in the future, if any of you know like Elon Musk's Neuralink company, kind of like that, I want to get into the research of kind of branching together biology and technology and AI for the betterment of humanity. Yeah.
Thank you very much, Samuel. Our next speaker is another James West scholar. We have Naima Adan.
Hi, everybody. Yep, so thanks, Cami, and thanks, Samuel. So my name is Naima. Oh, can you hear me?
Yeah.
Cool. So my name is Naima, and I'll be speaking about my PhD and kind of like my journey into my PhD, but I'll also be doing, so my presentation will be twofold. So the first half will be speaking about the scholarship scheme, and the second half I'll be speaking about my research project. So yeah.
Where's the clicker?
Okay, so I think I'll just very briefly explain like what I did prior to like joining the PhD project that I'm on. So I worked in 2018. I was a biomedical researcher for a company in Sicily looking at pollution of the sea and kind of like rivers there. Then I was working on a project looking at Bardet-Biedl syndrome and admin in kidneys. And then I was a chemistry technician at a sixth form for about a year and just like start of the pandemic. And then I was a locum biomedical scientist for a year and a bit actually, but with locum you're able to just kind of very much pick your own hours, and with the pandemic it was helpful. And then in 2022 I joined Imperial College as a staff member doing public engagement work. So I specialized in looking at underserved communities and minoritized communities to try and get them more involved in research to better understand what the communities need. And then 2023, I joined the Hashimi Lab, where I started my PhD journey. So at the start of the pandemic, I signed up to do my MRes here at Imperial, and it was through student finance that I funded it. And then roughly around that time as well, I got into coding. So I'm learning different programming languages, so like HTML, CSS, Python. So why I did the MRes was because I wanted to kind of like explore looking at biological problems and seeing if I could use engineering principles to kind of try and solve them, but also explore coding a bit more and kind of like develop that skill. So yeah, so I was searching for PhDs, and I was ideally looking for something that had like wet lab element to it, but also had a computational element that was in neuroscience. So I had like all of these criterias, and they were quite hard to. It was difficult to find a scholarship or like a program that kind of answered all the questions that I needed and kind of like all the goals that I wanted from my PhD. Until I found the James West Scholarship through Perry. Thank you, shout out Perry, and. The scheme is quite interesting because it very much addresses some of the points that Kemi made earlier about like the lack of representation in these spaces, and that like the black population make up less than 1% when it comes to like being awarded PhDs and even just like the positions themselves. But then it carries on till professorship, for example, is still less than 1%. So the amazing thing about the scholarship is that it doesn't just give you funding. Like I think Samuel very much like briefly covered it, but when it came to doing my MRes, I had to fund it through student finance, and even then, the money that you get awarded is very specific, and my master's wasn't fully covered by that, so I had to try and get like an external scholarship whilst trying to like maintain living costs and like obviously paying for rent and everything. But with the scholarship, you're able to get that 1 year of the master's of research as well, and then funding for your PhD as well. But what also comes with the scholarship is like this sense of community, which I've heard like from like when I was doing my MRes, especially during the pandemic, it was very isolating. And I can only imagine, obviously, with a PhD being very independent work, it can be even more isolating, especially if you don't have like a community or like a good group of people around you. So that is something else that the PhD offers, is a mentorship and mentorship and all of that. But yeah. So a little bit about my research. So I'm exploring the gut-skin-brain axis to look at serotonin detection and very much looking at the relationship there. So the big question for our research project is, or like the big question that the Hashimi Lab looks at, is depression. And over 300 million people have been diagnosed with depression, I think it was last year, and the numbers are increasingly growing. And when it comes to depression, when it comes to the diagnosis of it, like we're expecting somebody who's obviously not well to be able to go to the doctor and very much explain how they're feeling, what they're feeling. And it's like this checkbox of like things that are very subjective to whatever the clinician is seeing. So because there's such a big global burden when it comes to depression, what we're looking for is a way of specifically testing for depression, seeing like if we can chemically identify that this person has depression. So let's move on. So I'll quickly talk about the depression hypothesis, which is that serotonin, norepinephrine, and dopamine are three neurotransmitters that have been identified I'm going to go back. So the monoamine hypothesis is that these three neurotransmitters are depleted when it comes to depression, but we have actually no way of testing what's happening in the brain. So what we're trying to do is kind of like explore these axes and see if there's a way of measuring it through other parts of your body, because you obviously don't have access to your brain. So one of the platforms that we're kind of looking at to do this is looking at the relationship between your gut and your brain, because we obviously know that there's a bidirectional relationship between your gut and your brain. So ideally what I'm trying to do is create a platform that I'm able to put 3D organoids on the chip that will be able to measure the levels of serotonin, norepinephrine, and dopamine, but I specifically look at serotonin to see the measurements and see the relationship between the gut and the brain when it comes to depression. So ideally, my two main aims are investigating the brain-skin inflammation axis and also investigating the gut-brain inflammation axis. So this is the technique that we use. So it's called fast scan cyclic voltammetry, and ideally we use a carbon fiber inside a glass microelectrode to take the measurements when it comes to the neurotransmitters. But yeah, actually I'm done. So thank you.
Thank you so much, Naima. Does anybody have any questions at all? Okay. Might need to leave these up and around. Could you pass this back there, please? Thank you.
Thank you. Hi. How do you use coding, if at all, in the work that you're doing now? Like, how does it relate in your work? Like, what do you use it for?
Thank you. So currently, I'm not doing too much coding, but I am in the process of designing the platform that we want to use. But that's more kind of like dimensional designing. But the idea is that after, like, in the next coming year, that we have enough data that I'm able to kind of like use like data analysis and kind of like modeling and see the relationships and see if we can find a path then. But ideally, probably be using Python, hopefully, in the near future. So probably definitely just to like analyze the data that we get, because you do get like a lot of data from these calibrations. Yeah.
Any other questions?
Yeah. What was the greatest challenge that you faced when you were approaching your PhD?
I think the biggest challenge that I faced is that you probably can get into a PhD program. and that like you can probably find research that very much aligns with what you want to do. But I think the biggest challenge for me was finding the right environment, and I think that's very much where the scholarship comes in. Yeah, so finding the right environment, finding like a group of people that actually very much care about your betterment, not just like academically, but in all other respects and regards. So, and I think, thank God that I did find it, because I think if it wasn't for that, if it wasn't for like all my goals aligning, I probably wouldn't be doing a PhD, and I don't think I would have done it if it wasn't for the scholarship, because you can find research anywhere, but finding a good group of people to be around is sometimes difficult, especially if you're not in the environment already. But yeah.
Okay, great. Thank you so much, Naima. And next talk is...
That's not connected, so they need the clicker to change the slides.
Okay, well, where is this slide? Clicker. Does anyone know where the clicker is? The presentation clicker?
Yeah.
Okay. Well, the next person that's going to present is Peter Bryan. He is the final James West Scholar.
There's a screen here.
Thank you very much, Peter.
Okay, hi, yeah, I'm Peter. I'm going to be talking a bit about my PhD and the work I've done so far since starting in January. So I'm in the neuro rehabilitation group, which is actually at Whitesea, not here at South Ken. Dario Farina is my PI. And the focus of the group is, well, it's quite a large group, so there's a lot of different research directions. You can see some of the areas at the bottom of the screen there. But the main focus is measuring and acquiring signals from the brain, the nervous system, and the muscles, and using that in combination with motion capture and limb surface reconstruction to study the neural control of movement, specifically for people with movement disorders such as stroke, Parkinson's, or spinal cord injury, in order to guide rehabilitation methods and to develop assistive technologies to help these people. So the principle that rehabilitation works on is neuroplasticity, which is where the brain can rewire itself and develop new connections with different areas of the brain. This happens normally, like in healthy people. For example, when you learn a new skill or you do a sport. But it also happens if someone has an injury. So if, say, in a stroke, part of your brain is damaged, the brain can repurpose different areas of the brain to restore the lost ability. So for example, people lose their speech, and then after rehabilitation, after some time, they can learn to speak somewhat again. So by studying the signals that I talked about in the previous slide, we can hope to improve rehabilitation methods and enhance the recovery and speed up. So the rehabilitation methods that are used at the moment, it's very similar to learning a new skill. So having a lot of repetitions and the more time you spend doing it, like if you're learning an instrument, for example, so that's the same with rehabilitation. And it's very time intensive. You need to have guidance from someone to make sure you're doing the right exercises, right techniques, and you're performing them properly. So it's a lot of demand on therapists, one-on-one with patients. And it's also quite physically demanding as well. So for example, for lower limb, like gait training, it's a lot of, you sort of need to move the body of the person and take a lot of the weight, which is very physically demanding. So the use of robots in rehabilitation has been sort of increasing, particularly in the last 20 or 30 years. There's been a lot of research in it, and using robots in place or alongside a therapist to help with rehabilitation. And there's a key part of that is how the robot is actually controlled. So we can study how humans interact with other humans, and then take this and apply it to the robot and look at how humans interact with a robot in terms of rehabilitation, and seeing how changing the control strategies of the robot can affect rehabilitation. Okay, so this is the area that I'm actually focusing on for my PhD, which is developing soft exoskeletons, which are also called like fabric exoskeletons or exosuits. And basically, instead of, so like an exoskeleton you might see in films like Edge of Tomorrow or Elysium, you have fabrics instead of the rigid links. So instead of like effectively a robot that you're wearing, it's more like fabric, like clothes that you'd wear, or a brace if you like strain a limb or something like that. It's got quite a few advantages. For example, it's cheaper and lighter, so you could wear it daily and it'd be more comfortable. And the purpose of it is to help take some of the strain off the therapist. It can, so for example, if you have it for upper body, it can take some of the body weight off and make it easier to perform rehabilitation exercises when you have some weakness in the affected limb. And also, if you make it comfortable enough to wear during the day, you can assist people just during normal activities. So not just within the rehabilitation, you can actually make it easier for them to perform tasks like throughout a day, which helps with the rehabilitation. So yeah, there's some specific challenges that you come up with when you're using soft or like using fabrics instead of rigid links. You can't have as high forces, and it's quite important to think about like the transition between like you're applying a force in a particular point, but you need to spread that force out around the limb so you don't end up with like uncomfortable or like pain within the skin. The devices that I'm sort of prototyping at the moment use cables and motors to pull on limbs and support the weight. There's a few different, like there's other groups that use pneumatics instead. Go on to the next bit. So this is the work I've done so far. There's a lot, well, I started in January, so there's a lot of background reading initially, like, which is the same with most PhDs. You need to get up to date with the field, understand what everyone else has done, so then you can decide which direction you want to go in and make sure you're doing like novel research and you're not just repeating what someone else has done. And then it was a planning stage, deciding like, right, this is what I want to try and achieve during my PhD, this is the direction I want to go in. And then started some prototyping, sort of hands-on, because my PhD is quite, well, at least at the moment, is a lot of actual hardware development. You have some PhDs which are a bit more software or just sort of full research. And then I had a period of time where I was actually working with other researchers in my group, like more than working on my own PhD. So collaborating with their experiments, which is very interesting, and actually like a part of the PhD that I really like is you're working in this group and they're all working on cutting edge research. Well, actually, I'm gonna talk about this in the next slide, so I'll go on. And then the next few steps of the PhD, like we'll see as we get to them, but is developing more of the device, looking at how to incorporate a bit more sort of generative algorithms to, thanks, Kemi, to in the design of the device, and then also some data collection and the design of the controller for the device. So some things that I have not enjoyed so much about the PhD so far is Samuel said earlier, like one of the nice things is you're responsible for the work and like it's your work, but on the other side of that is like you're fully responsible for it. So like, yeah, like you have to do the work. If you're not turning up and you're not doing it, like that's when you get to like your second or third year and you'll be like, oh, look, look who hasn't been doing my work. Oh, it's me. You also get it like, you go through stages, especially when you're stuck on a problem and you're just thinking about it all the time. Like you go to bed and it's the last thing you think about. You wake up and it's like, it's just there all the time and you feel like you're not making any progress. So you go through these stages of finding it really difficult, but then you have a lot of positives as well. And also, if you have a good group around you, it can help a lot with things you struggle with. But yeah, you have complete freedom to choose what you want to do in your PhD. So you can say, oh, I really want to learn about, like Sam said earlier, I really want to learn something in AI, or there's like a particular coding language I want to learn. I mean, this is the last slide, so. So then you can guide your work towards that and say, right, I want to learn this, so I'm going to take my PhD in this direction, and then I'm going to learn that. There's a lot of collaboration with other people in the group, and like throughout the university as well. Then you have a lot of opportunities to go to conferences, like in other countries, and you can see other people working in your field in slightly different directions. There's a lot of like opportunities to see really cutting-edge research that you see in the news comes out, and it's really exciting. You're like, oh yeah, I know the person who wrote that paper, or the group that's working on that. So that's it.
Thank you. Does anyone have any questions for Peter? Okay, we have one down here for us.
So part of the recovery process when you have an injury is to gradually sort of increase the muscle's ability to move and to get stronger. But if you're sort of mitigating the workload done by the muscle by using an exoskeleton, do you find that the recovery process increases, or is there such a minimal sort of mitigation that it doesn't affect anything?
Yeah, so that's like an important part of the control like that you're using for your robot. Obviously, if you just take the full weight of the limb and the person doesn't have to do anything at all, then you're not really going to provide any rehabilitation, because you're not building this pathway, you're not like actually inducing or using any neuroplasticity. But if you have it to the amount where you're just sort of helping with the movement and you're not fully taking over, then you can get some good rehabilitation from that. There's actually a lot of research into how to tell when someone is like engaging with the task, like when they're actually trying to move their muscle, as opposed to just like letting it happen for them, and then using that to guide how much assistance you're giving them. So yeah, thanks for the question.
Oh, lots of questions. Okay, I am going to, and then if you could please give it to him next one.
How did you find like sourcing out the fabrics to use, and like what criteria did you think for it?
So it was kind of a new, like there was one postdoc who had been working in a similar field, but he hadn't done a lot of actual hands-on like development of the task. So a lot of it was literally just like going to a fabric shop, looking around, like you're like, oh, I know I need it to be this. I know I need like a certain amount of stretch in this direction or that direction. It needs to be like, or not have any stretch, or it needs to be strong. And then you iterate through a lot of different things. It's the same with any design task. If you're building like a robot, or you're building like a soft exoskeleton like this, you go through a lot of different iterations. You try something you think is going to work, and it just doesn't at all. So you go on to another thing and you build on that. So yeah, thanks for the question.
Did you do any work with neuroscientists and other things like that to make sure that muscles were engaged, or was it just physical tests?
So we haven't started gathering data yet with the devices, but the group that I'm in has a lot of expertise in like rehabilitation. So, and we also have some collaborations with like therapists and doctors who are working like actually directly with these patients. So there's a lot of expertise coming in from different areas.
So you said before that when you started doing a PhD, you did a lot of background checks to make sure like no one else is doing the same research topic as you. Did you find that like when you were originally coming with your idea of what to do for your PhD, that someone else was doing the same thing as you, and then did you have to change, or did you come up with the idea yourself? And if you did, what inspired you to pursue that research topic?
Yeah, so that's something I think quite a lot of people get when they're doing like literature reviews, like reading through what everyone else has done. You have this idea in your head, you're like, oh, this is like the best idea. And then you read through and you're like, no, someone's already got to it before me. Or you kind of like, you almost don't want to read too much because you're like, oh, maybe I'll find someone who's actually done what I want to do. But if I don't read it, then it's fine, I didn't know about it. But you actually get a lot of inspiration from the things you read. And one of the skills you get from reading lots of things is saying, right, I read this paper and it sounds amazing, sounds like they've solved the problem, but actually they're just presenting the very best of what they've done. So you get the skill of reading it and going, oh, right, I can actually see what didn't work, what still needs to be addressed, what they didn't do, what they're not actually talking about in the paper. So you get a lot of inspiration from what other people have done or haven't done. Yeah.
Hi. After doing all that research and spending all that time and hopefully publishing a paper, do you get paid for it or?
So PhDs typically are you don't really get paid for them, but you get you basically get enough money to live while you're doing the PhD, but not a lot more than that. So when you publish a paper, if you're wanting to go into academia, it's really good to have papers published, and then that's how you get a good postdoc position. You go on to be a lecturer and a professor, and then that's when you actually start to earn a bit more money, but a little bit more money. Doing a PhD is, you're still learning. It's kind of like doing a master's or undergrad. You're still learning to be a researcher. You're not, which is something I kind of missed a bit when I started mine. It's you're not expected to get a Nobel Prize for your PhD work. You are still learning to be a researcher. You're not I don't know. Yeah, it's very much something you're learning in and not getting paid a lot, I'm afraid.
Final question for Peter, please.
Yeah.
Is the technology supposed to be used purely to rehabilitate people, or can people with Parkinson's, for example, use it long term?
Yeah, so that's a good question. It's we're primarily looking at it to be a rehabilitation device, but one of the big benefits of it being soft and being something you could just wear and it wouldn't be super obvious or heavy or uncomfortable is you can just wear it throughout the day. So it can be an assistive device instead of just a rehabilitation device. And then because someone is having this help with their movements, they're actually going to use the limb a bit more. So say if they have a lot of weakness in their arm, they're probably just going to use the other arm for daily tasks. But then if you have this device on and you can use your affected limb a lot more, then that is going to still help with the process of rehabilitation. So it's kind of assistive, but you're still having the rehabilitation. And that's when the control strategy, how much assistance do we give the person, comes in. That's when it's really important. Yeah, good question. Thanks.
Thank you very much. We're now going to hear from Salu Pujet from the University of Surrey.
So I was given the topic, what is an engineering PhD? I'm a chartered engineer, so I'm always in the field out there. But I'll tell you why I actually decided to do PhD. I'm also a project manager during the day. So my week is normally divided into 2. 4 days working as project manager, the 3 days I try to balance it as a researcher. So to answer the question, what is an engineering PhD? I've decided to ask myself some questions. What is the research I'm doing? Why am I doing it? How? And later on, you might probably agree with me that it is an engineering PhD. So I'm trying to assess infrastructural resilience in small water supply. And the key area I'm looking at are the functionality of a hand pump, substandard materials, seasonality, and coping mechanism. I'm also looking at corrosion of hand pump, and I'm a member of the forum called Stop the Rot. I'll come to that later. So why? 2019, I was working as a senior project engineer on the HS2. Then my manager came to me and said, there is a project in Sierra Leone, and I'm a native of Sierra Leone. He said, I want you to go there as a package manager and lead engineer. You have complete ownership to install 2 service reservoirs and 6 kilometers of pipeline. And I said, yeah. So I went to Sierra Leone, and I looked at the water system. It was so bad. 20% of the city cannot really get water. But it was also one of the best systems I've ever seen, because the whole system works on gravity. So the water comes from the dam, comes out to the treatment center, it gets treated, enough pressure, goes to the distribution center, still enough pressure to supply the whole half of the city. But it never works that way. So I remember in one of the senior management meetings, I went up to one of the guys that was very high because it's government owned. I said, if I was running this company, I said, I would not only I'll be supplying half of the city, I said I would make a lot of profit, because we don't really need massive pump to pump water into people's home. And he said, you don't really understand. You just seen what is on the surface. And that actually triggered me to go on and to start researching. So when I came back to UK, I started researching, but I was just focused on Freetown, which is a city. And I'm also a victim anyway, because anytime I'm in Freetown, I don't get water in my house. So I thought I might solve the problem as well. But then as I started reading literature, I realized the problem was much worse in the rural community than Freetown. I realized that 500 million of people in sub-Saharan Africa, they depend on groundwater source. And 1 out of every 5 of those people, they depend on the hand pump. And I think we have about 700,000 hand pumps, and most of the time, 30 to 40% are non-functional. So I really wanted to understand why, and probably help to improve that. So as you can see, if you look at the population of the rural population relying on borehole and protected well, I'm from Sierra Leone. Yeah, I'll come to that. But just close to Sierra Leone is Guinea, is 57%. If you come to Sierra Leone, proportion of total population relying on hand pump, it's not that massive, it's 34%. But there's a story behind that I'll tell you later. And so I said, okay, there's still a good number of people, 34%. Still not getting enough water. And then I decided I wanted to change my topic redefine my topic from really looking at Freetown and just look at rural community and how that happens. And then I collaborated with a French non-governmental organization called Imperial to say, listen, I still want to understand the rural works, but then I really want to go on a field trip to really hear from the people in the community. And so I undertook a field trip. So I went to Makama Chiefdom. We went to 3 different chiefdoms. In Sierra Leone, we've got districts and we've got chiefdoms. So in most chiefdoms, they have up to around 80,000 to 100,000 people. So I went to Makama Chiefdom. In Makama Chiefdom, most of the people rely on pump water. And there were 4 water points. That's the hand pump. And what I found so astonishing was that for 3 months in a year, the pumps goes dry, no water. How did they survive? Again, that's where I'm looking at the coping mechanism. So they go to the nearest swamp, they dig swamp water. That's what they use for 3 months in a year. As an engineer, as a chartered civil engineer, I know what the problem is. I know how to solve the problem. We can easily rehabilitate that and solve the problem. But then I have to look at, it's not 1, it's not 2, it's 44 water points that serves the whole community. But I wanted to know what went wrong. Is it pre-construction? Is it just construction methodology? Or is it the timing of the funding? Because most of these pumps are funded by non-governmental organization or UN. So again, that is literally taking me there. I spoke to most of the people that work there and say, what do you think is the cause of this? And they say, well, I know, as an engineer, I have engineer instinct that most of this water in Sierra Leone, we've got the rainy season and the dry season. And most of this, we are constructed in the rainy season. And because it was constructed in the rainy season, in the dry season, the water table goes down. So in the rainy season, they don't have to go very deep, there is water. In the dry season, it goes down. When I read literature review, most of the literature review I read was just to do with global warming or temperature. But 44 water point, no, it doesn't make sense. You can't have 44 water point in different locations or going dry for 3 months. But then also there's another problem. I'm also a group of another forum that has to deal with hand pumps. They call Stop the Rot. Again, with these hand pumps, they've got, they are very aggressive water system. For example, if you install a galvanized iron in an area where the water level is below, pH level of the water is below 6.5, it gets rocks. With all pump materials, if they are installed and permanently submerged in water, at some point, they will get corroded, but not as fast as this we are. So again, what I'm trying to do with this, I'm much more concerned about the substandard materials. When I spoke to the local engineers, I said, you work with these people all the time. What do you think is the biggest problem for the non-functionality of hand pump? They simply said, substandard materials. And that actually created an extra demand for me to say, well, I really want to look at these substandard materials. So what I'm going to do with these standard materials, I'm going back to Sierra Leone by the end of the year. I'm going to get some of those materials. I'll bring them to the lab in Surrey, and I really test them and subject them to different conditions in the lab. So really, for me to have an evidence to say, sorry, must have an evidence to say, yeah, they're really the cause of what's happening. So methodology. There are definitely two areas. When I did a field trip, I really enjoyed speaking to the people, talking to them, knowing what the problem is. So I'm still going to do part of the functionality and the seasonality. I want to know, how do they cope? They just told me, I was in a rush. They said, well, 3 months, we just go to the nearest swamp, dig a well, and that's how we get water. But I want to go back really and speak to them, have focus group, interview them, do survey. But on the other hand, on the substandard materials, I think that's the biggest problem. In Sierra Leone, there is no standard. So myself and you can open the shop tomorrow, we start producing material, sell them, nobody questions us. So I'm going to bring them back to the lab, retest them, and really have an evidence to show that they do, in fact, impact the materials, the functionality of hand pumps. And this, my people, is an engineering PhD.
Wow. Thank you. Does anyone have any questions for Salu? Okay, can you just pass that down? Thank you.
I wanted to ask how easy or how common is funding for a project like this, which isn't super applicable in the West and is sort of very regional to sub-Saharan Africa?
Sorry, I didn't get that.
So how easy or common is funding for a project like this, which is very specific to sub-Saharan Africa and not super applicable in the West?
I think for Sierra Leone, I've not really spent a lot of time in Sierra Leone, but I think for most of this hand pump, there is also, there are fundings, but most of this, for example, in Makama Chiefdom, 44 is not working. And when I was there, they were already trying to get more funding, to get more water points, but that's not really solving the problem. So I think, I don't know much whether the funding on this side is better than in Sub-Saharan Africa. I know there are a lot of fundings. I know there are around 700 hand pumps there. And I know most of the time, 25 to 30% are non-functional.
Any other questions?
What do you mean by seasonality?
Okay, so in Sierra Leone, they've got 2 seasons. They've got the rainy season and the dry season. So in the rainy season, there's no problem with water. There's rain, there's water everywhere. In the dry season, there's less water. Like it's literally divided into 6 months. 6 months of rain, 6 months of dry. So at the peak of the dry is around March to June. So during those times, if you go to Makama, you will not have any proper drinking water, or you not get water from the water point.
So with the water system, have you been working to fix it, or is it completely fixed now? Because I remember you talking about it.
Yeah, in the freezer water system, yeah, I work on the project, and we did rehabilitate the system there. But it's a problem that is just recurring, because we've done it, we've come back, a couple of years, somebody else has to go back and rehabilitate it. They've not really been able to keep maintaining it, maintain the system, Like I said, if I was running the system, I'm very sure not only will I serve half of the people, but I'll be making a lot of profit because the system works on gravity. But I'm not running the system.
Okay, thank you. Apart from some of the errors you detected, that might be responsible for the wells to run dry, don't you think there are some other human factors or human errors? Something like pumping a particular aquifer aggressively from different pumps, from different locations. It's not possible to make those wells to go dry. Thank you.
Yeah, I was just looking at one reason, and I was looking from the perspective that if I was to do this as an engineer, what I have to do is to rehabilitate it. I know one of the reasons is it was probably done during the rainy season. I know if I do it at the peak of the dry season, and I know if I can get water at the peak of the dry season this year, next year, maybe there's an effect of global warming, but at least, I'll reduce that time from 3 months to probably 3 weeks or 2 weeks. But there's very possible there are other reasons.
I know that you're applying to test different metals in order to reduce the rust. But wouldn't that just slow down the situation, since it's going to be metal, it's going to rust eventually, since it's in water for a long duration of time? Is there an exact solution, like using different materials like plastic or something else?
Yes, correct. We've got different manufacturers of hand pump. We've got the India Mark II. They mostly use galvanized iron. Then we've got the Afridave, which is mostly made in Africa. They use rubber, plastic, and it sounds better than the India Mark II. But the India Mark II is very common, and it's everywhere in the market in Africa. It's very easy for you to buy one than the Afridave. There's also a plan for us to, I'm part of a team as well that is working to try and standardize the hand pump, the SI unit for the hand pump. And we're looking at really just seeing whether we can then move towards just stainless steel. Again, because those components are permanently submerged in water, at some point they will get corroded, but then it will take time, not at the rate at which they are now at the moment.
Got time for 2 more quick questions. Hi, I was gonna ask what are the benefits of being a chartered engineer as opposed to just having a master's in engineering or a PhD in engineering?
Well, I'm a chartered engineer, Institute of Civil Engineer. It's very difficult to get, but also I get paid very well. That's the reason why I'm doing my PhD part-time. Because when I started doing PhD, I thought, can I just take 3 years, 4 years to just do PhD? And I then calculated how much I would lose out working in the industry, and I thought, no, I'm just going to do this part-time, and it still works, because mostly I just manage a couple of projects within central London, so I kind of like manage my own time. I'm not always on site. I work from home a couple of days. I only go to the head office once, and then if I've got active project on site, probably do 2, 3 visits in a week, and most of the time that then allows me to do my PhD and still do what I want to do.
Okay. You're quite popular, so we're going to allow for a few more questions.
You've touched on some of the points, but following your research, what are the next steps? How do you reimagine the future for Sierra Leone?
It's very difficult to say. Like I said, some of the system, if I was running it, I know definitely I will serve a lot of people and I'll make profit. I couldn't really understand why, when I spoke to the senior manager back then, he said, I didn't understand what the problem was, because I did. I'm an engineer, I'm a chartered engineer. I know how the system works. There's water from the dam into the treatment center, and then get on from the treatment center to the distribution center, and it's only the presidential lodge that get where the water is pumped. Every other where is they get water through gravity. But also I know why they don't get the thing is from the treatment side to the distribution center, the people in between that area do not get water. So how do? They tap into the main spine. And so the main spine is always. There's water everywhere, every day. So when I went there, part of our rehabilitation, my package, which I was managing, was to try and build 2 new reservoirs between the distribution center and the treatment center, and then ensure that those people within those communities, they are served, they get water. That would then solve the problem.
Right, thank you very much for your presentation. My statement is not even a question, it's more of an addition to what you said. Yes, I do agree that substandard materials could be the cause, but I took an expedition to Nigeria about 20 years ago, year 2000, and what we found in some of these pumps is lack of maintenance. Galvanized steel is very, very good, provided there's no standing water on it. It will not corrode. It's designed for that. It could last hundreds of years. So what we did is to go in there and encourage young boys and girls sitting on the street doing nothing. We train them on now to repair this pump. It takes half a day. We bought them the tools, they get the pipe out, flush them out, and they put them back out, water flowing. It's very, very simple. So what I didn't like about the people that installed the pump in the first place, they just went in there, whether it's a World Bank, whoever, installed the pump. Oh yeah, there's water for everybody in the village, but they don't actually train them how to maintain it.
Correct.
And that's one thing I think you should look at as well.
Yeah.
Training the locals to maintain the pump.
Yeah.
Okay.
We have one final question.
I was just going to ask, what's the process to become a chartered engineer?
Oh, Lord.
So first you need to get, most times, the route I took, you need to get a minimum of master's degree. And then they've got what they call IPD, so initial progression development. And then you then do that for 3, 4, 5 years. If you're lucky, really work on some very good projects, and you have your company support the system. And then you then have to get all your IPD signed off, first of all. That's very difficult to do. Most people spend 4, 5, 6 years doing that. And then you then apply for your chartership. You then have a review where you have mostly 3 people that will review you, 0 conflict of interest. You attend the interview, and it's mostly 70 minutes. And then you've got to write, they've moved in now it's communication task. You've got to write around 1,000 words in less than, I think, 90 minutes. And they're very particular about grammar as well. So, yeah. But it's quite a difficult process. If you go through ICE, there are other members that are not difficult as ICE, but ICE and I/E, their process is very, very difficult. So it takes a lot of time. The minimum from university, when you get your master's, to get in the chartership is normally 5 years.
All right.
Different routes as well.
Yeah, exactly.
During the break,
Yeah. So that's a point I wanted to make as well. Don't forget that we have breaks and we have a networking session with food, drink, music afterwards. So all of these questions, if you don't get to ask them now, do save them for afterwards. Make a note in the notebooks that you've gotten so that you can ask questions of everyone who's speaking today. Thank you so much.
Yeah.
And we're now going to hear from Sunshine Iguodala from Imperial.
Hi everyone. My name's Sunshine Iguodala. I'm a second year PhD student, so I work in chemical engineering, so slightly different from what you've heard. And my PhD is industry funded, so again, quite different from some of the previous presentations you've seen. I work on polymer membranes for CO2 capture. You've probably heard quite a lot recently about the increasing CO2 emissions across the world. There's expected to be about 250,000 additional deaths per year due to this kind of climate change, particularly the increase in CO2 emissions. And you might again have seen some of the flooding in Nigeria and Pakistan. Climate change disproportionately impacts the global south. But if you see who the greatest contributors are, mostly America and Europe. But yeah. So CO2 capture is a technology that's relatively new. You want to capture the CO2 and then store it, and then it's used in other applications, other chemical procedures. Currently, amine absorption is used. This is a pretty energy-intensive process. So we use kind of an amine solvent. It absorbs the CO2, but having to then remove that CO2, there's a lot of heating, cooling, pressurizing, and that, of course, is going to bump up your operation costs. And as well as the amine solvent, over time it degrades, and as it does this, it releases various other chemicals, such as heat-stable salts, and these have a whole other environmental concerns with this. But I am working on using polymer membranes to separate the CO2 from industrial process flue gas. So it has a mixture of CO2, nitrogen, other nasty gases, and water as well. What's a good thing about this? This is energy efficient process. So it runs at ambient temperatures. You're not having to use like really high temperature, so that's really good. This means lower operating costs. There's a reduced environmental impact because the amount of materials we use are a lot less, as well as this kind of the process steps of doing this is a lot less as well. So, but one of the big things, it does require further development. So one of the things that I guess chemical engineers working in this area struggle with is kind of finding a balance between the selectivity of these membranes, so how much they like a specific gas, let's say, and their permeability to a specific gas, so how easily a gas flows through the membrane itself. So you want high selectivity and high permeability to a specific gas. Yeah, that's kind of what you want, but it's quite difficult. So I actually come from a chemistry background, like hardcore organic chemistry. But yeah, now moving on to chemical engineering and seeing kind of using my skills from chemistry itself. So I work on the synthesis of polymers. So it's like a chemical just repeated loads of times. And we use these really interesting ones. They're called polymers of intrinsic microporosity. So they have these flat ladder parts, and then they're connected by these spiroatoms that cause these structures to kind of kink, and then they don't pack very efficiently. So there's like loads of gaps within this, and these big gaps is called free volume, and this allows certain gases to pass through very easily. What's a great thing about these polymers, you can add different functional groups, so let's say different chemicals onto them, and they can make them more selective to certain gases. So you can add, like, say, fluorine atoms or some of the amine atoms, amine groups, and they can, yeah, they like CO2 more, so you'll get higher CO2 permeability. So one of the kind of problems with this, to a chemist, this is great, but to a chemical engineer, they kind of hate this. Lots of steps, and this means that you can't scale up, and it's not cheap, and yeah, not great for a chemical engineer. So one of the things that I work on is simplifying the synthesis. So in my first year, I was able to kind of simplify this completely to one step. So you use an aldehyde or ketone, and then you can use a spiro group that has either two OH groups at the end or two ether groups, and you just put them in one flask, and you're able to get, unfortunately I can't show any structures, but you're able to get really nice, robust, flexible films, which is what you want for these processes. They're easily scalable, so a chemist, you really enjoy getting milligram scales, but we can do this 100 grams pretty easily just in the lab on your own. And they also they fall within a hydrophobic range. So I don't know if you remember I said some of these feed gas streams, they have water. So you need to make sure that some of your films are hydrophobic to stop kind of competitive sorption of different gases. So this is kind of what you want. And another good thing that makes chemical engineers very happy, it's quick and costs very little. So yeah, that's what you want. So then after you get your membrane or your film, this is quite a small one just for testing in the lab. It's pretty thick. We're able to put them into rigs. So in our lab, we build these gas permeability rigs. You can load your membrane in, you can test them at different pressures, different temperatures, almost to kind of simulate the sort of conditions that you would have when you in these kind of process plants. You can do mixed gases, you can add a humidity control, so you can really kind of get the exact, you can find out exactly how your membrane will perform in the real application. So just comparing that to kind of one of our most recent ones, so PBACs and polyactive polymers, they're commercially available polymers, they're really expensive. So, I mean, they work great, but yeah, expensive, so kind of not what we want. But one of our new PIM-based polymers, we are able to get performance that is comparable to some of the commercial polymers available, and it's significantly cheaper. But one of the most important things moving into, again, a common thing, I guess, within engineering is always kind of moving it to commercialization. So most films and most literature, they report the performance of their membranes at really thick, when they're really thick, but actually we want to reduce that completely significantly, and this is what we're able to do with a lot of our polymers. We can, so this is a SEM image, it's like a microscope image, very, very strong, and you can, yeah, you can't even basically see it with the naked eye. So yeah, it's very thin and works very well. And another thing we do is we are able to build models of our polymers. So this is what I'm also working on now, is we can take the different monomers and we can put them into a box, let's say, and then we can force them to form a polymer, and then we can do a whole load of other tests on them. So for example, this is PIM1, it's one of the polymers I showed before. We can build the polymer chains, fill them into this box, and then we do something, it's called annealing, where we then compress it to experimental like densities, because obviously doing something on a computer is not exactly as it would be experimentally. So we're able to put them in the box, compress them, and then we can extract some structure property relationships. So for example, this is some work done that I want to do with some of my polymers. We can feed different gases in and see what the interactions are between the polymer matrix, see what groups like certain gases, and just see how they behave. But one thing to kind of realize, I'm like at the membrane material side of it, there's a whole load kind of different steps to this process. So I think this kind of graph really shows how much of like a multidisciplinary process it is. So you've got kind of chemists working on the materials and material scientists, but also you need engineers, mechanical engineers and other chemical engineers working on like process design. So you can have a good membrane material, but it's at the beginning and there's a lot of work involved. I just want to thank my research group. So we're quite a big group. And also, as I said, I'm an industry funded. So if you do end up doing an industry PhD, you get to go into an industry environment, try that out, and you get to be part of even bigger groups that work on even greater projects. Thank you for listening.
Thank you. Does anyone have any questions for Sunshine?
You said you were industry funded. So with that, how long does it take to actually complete the PhD itself? Like, does it take longer?
No, it's exactly the same length, but you basically have to deliver what they want. So, yeah, I guess maybe it's a little bit more pressure because they're paying you and they're saying, okay, we're paying for everything for you, but you can't come out and say, oh, it didn't work. They kind of want something at the end and they want you to solve their problem. Yeah, so, but it's the same length of time, but you have to give them something.
Because you're getting a PhD through the company, does that mean that you don't have ownership of the patent?
Yeah, that's interesting. There's other ways to go around it. If you ask my supervisor, he'll probably have some great, I don't know if I should answer that. Yeah, so for certain projects, so with Schlumberger, I work on like materials for one of their IR sensors. Anything that comes out of that is theirs, it's not mine. Other projects is different because I'm funded by other things as well. So like Sinhai Cell, it's a big project spanning 6 universities. They fund other projects that I'm doing. So with that, you can think about patenting and things like that.
With your formation of the polymers, you use the simulation. Is that a limiting thing when you're kind of working with the chemicals, or does it slow things down, or if it doesn't, what software and hardware do you use?
Actually, it makes it better, mostly because you can kind of screen a lot of polymers. So if you think about, if you're in the lab, you can decide, okay, I want to put these 2 monomers together, and I think it's going to work really well, but in reality, that's not how just chemistry works. You kind of have to, maybe the monomer itself had a functional group in the specific place that doesn't allow the two monomers to form a polymer itself. So doing it through simulations, you are able to try a whole load of things out, and you can actually see which ones form polymers or not, so you don't waste your time having to buy materials and trying to work out the synthesis itself. This actually speeds it up. The longer part of it is writing the code, that's the only. But once you've got it working, there's loads of great kind of open access codes that you can use. If you are ever interested, you can read Polymatic. So this is kind of what we use to build our polymer matrix and structures.
Are you planning on making them reusable, or will they just be single use, so each time it's being done, you have to replace them?
Yeah, so, the membranes itself, you can redissolve them, you've got the polymer back, but in terms of their application, so we test things like their stability over time. We want to make sure that if we load a membrane into kind of a real application, it works for years and years. So what we do is that, for example, some of my polymers, every 150 days, I test the film, and I would like to see the performance be stable over time. There are some polymers that over time, they lose that free volume that I was talking about before, and this means that their permeability to gases decreases over time, but this is due to their structure. So yeah, you need to be kind of working on multiple things. So looking at the synthesis, how can you change the structure to help them to be more stable over time? So you'll find yourself making a polymer, you can go and test it, and then after a while you see it doesn't work very well, so you have to go back to the beginning, make a new polymer. Yeah, so lots of steps.
Logistically, what would you say are the differences of working with a company for your PhD, both in what did you have to do to set that up, and have you found it's more limiting, or it's more freeing as you have access to more resources, or how would you say it is as an experience?
In terms of finding the PhD, it's pretty much the same. I think there's a website called Find a PhD. That's where I found mine. So it's word in iCase. So it's an industrial. There's loads different ones available. In terms of any limits to it, I think, again, you have to give them something. You have to fulfill what they've asked you to do, basically. If it doesn't work, you probably should have a very good reason as to why. But yeah, you kind of have to deliver on the project. But in terms of as you said, access to resources. So Schlumberger, they're based, and they've got a research site in Cambridge. So every few months I'll go there and I can test my membranes in an actual sensor that they use in real conditions, and you get more, I'd say, realistic data that you would expect to see in the field. Yeah.
Time for one last question.
So when starting the project of capturing CO2, did you initially know you wanted to use membranes, or if not, why did you decide to use membranes?
I don't know. Well, my group's a membrane group, so it was membranes or nothing. So in our group, there's different, I'd say, applications. The majority of my group work on energy storage, so like redox flow batteries, all that sort of stuff. They use those membranes for that. You can also use them for water purification. So there's a lot of great papers on that, and also CO2 capture. So membranes, many applications. So if you're ever interested, it doesn't have to be CO2 capture. It could be loads of different other ones. Yeah.
Thank you so much, Sunshine. So our final talk in the What is an Engineering PhD session is by Sanjay King from the University of Bath. Please give it up for Sanjay.
Sorry, I'm an engineer. Give me a minute.
I have no clue, but it's got to be something.
Okay, I'll just have to stay in there.
Okay.
Anyway, if you could just pop that. Thank you. Don't break it, please. It's expensive. Good afternoon, everybody. My name is Sanjay. I'm a electrical electronic engineer by trade. I'm currently doing my PhD at the University of Bath in the Center for Bioengineering and Biomedical Technologies, or CBio for short. As you can see on the screen, my topic is electronics-enabled organ-on-chip devices for high-throughput drug screening applications. I know it might sound like a mouthful, but don't worry, it'll get easier as I go through. So my research, as you can see here, this is all one sentence. My research aims to create an electronically controllable organ-chip platform using an electroactive polymer membrane to improve the physiological approximation of current systems towards high-throughput drug screening. Yes, it's a lot of words. So for the rest of my presentation, just simply think tiny organ modules. That's the easiest way to explain it. So just think simple things that actually try to recreate organ function is what we're going to be looking at here today. And to do that, I look at a few different topics. So I look at cell culture and pharmacology, so kind of how to grow cells, how to culture cells, as well as how drugs interact with cells as well. I look at modeling and simulation, so I actually model these devices and see now how they actually work in practice, before then going on to design my own and fabricate them. Simple enough? Lovely. Don't worry, I'll break it down somewhere just in case. So my topic, as you can see, is very long in itself. So high throughput drug testing is kind of how you can make any process is high throughput if you can make it a lot simpler and do a lot more in a shorter period of time. So instead of doing 100 tests in an hour, think of doing 1 million tests within an hour. So that's kind of what high throughput drug screening is. And that's kind of important for my topic because drugs do cost a lot to create. So think of drugs costing to bring to market from 1.6 million to 4.5 billion for one single drug. The range there is because of the different drugs or the different kind of diseases you might be trying to create a drug for. The price then begins to vary, as well as how many failures you have will increase the price as well. The time to do this as well is quite large, so about 12.5 years to actually bring a drug from discovery all the way to market. So that's kind of another thing that we spend a lot of time doing. And one of the reasons for all of this is looking at different ways in which we kind of screen drugs. So the two main ways we do it now is in just having
Hello,
Petri
good
dishes
afternoon.
with cells.
I'm supposed to have a cake ordered.
Thank you. We just have Petri dishes with cells on them, or we have animal models that kind of try to replicate what actually happens in the human body. And those are kind of what are mainly used to decide whether a drug can be used on humans. So this is kind of the whole process of how drug development is done. So let me just explain a quick thing about this graph. So as you can see, on the y-axis, we have the knowledge. So knowledge is just kind of how much we know about the drug and how much we know about the effect it might have, or what it actually does to the body in itself. So you can see that as we go through the phases, knowledge kind of improves. And you can see at the bottom is the time it takes for each of these different phases. So I'll come back to this graph at a bit later date. So organ on chip is my usual catchphrase. But a lot of people kind of say, ooh, that sounds nice. We're going to create organs to replace in our human bodies. No, so this is an organ on chip in my hand right here, so you can probably see one on the screen as well. A more accurate name for it would be a microphysiological system, but it doesn't really roll off the tongue as well, and not many people are like, ooh. So yeah, I really like that bit of it. So these are meant to be like 3D, so they're actually microchannels within this system, which have flow within them, which is microfluidic, which is similar to what the human body is like. So along a membrane, it's nice and thin flow of different nutrients, different liquids across it. Another thing that they do that kind of is why we still use animal models is the continuous flow, or just having medium flowing across those cells rather than a Petri dish where they're literally just stagnated in whatever medium they're in. One of the good things that's why this is kind of something I'm interested in is because I'm an electrical engineer, I know about chips, and the main way to make things this small and accurate is using methods that we already have for making chips. And the material here that you can see here, which we do have a few of the materials that are coming through, is PDMS, and one of the good things about it is completely transparent when it dries, and is kind of very useful for optical microscopy, which is why we kind of like it. So I do a few other things. So microfabrication takes a few different looks a few different ways in my kind of field of work. So I do mainly soft lithography, which is the process you can see mapped out by the arrows. It's kind of complicated, and I don't only have 8 minutes, and I don't want to get told to stop, so I won't cover that today. Fluid dynamics, for a microscale, you kind of have to think of flow in a different way, so that's part of my project as well. I have to model flow on a different scale and different size, and kind of seeing what that does to cells and how they grow. So another part is cell mechanics, so looking at how cells grow, which is that picture in the bottom left-hand corner, just to see kind of what the flow is actually doing to those cells as well. Still with me so far? Lovely. So now for the actual part of why I'm doing it. I'm an electrical engineer, as I said. So I'm trying to recreate the different movements that are happening within the body. So things like, so I'm specifically interested in the gut, which is the main kind of section where drugs are absorbed, so within the intestines. So movements within the gut are like peristalsis, which move food along the actual intestines, segmentation, which actually breaks up molecules within the intestine as well. And these are normally known to be mechanisms that actually help with cell growth and actually how cells actually evolve into what they are, express different enzymes and stuff like that. So at the current moment, a lot of this is done through pneumatic actuation, so just using vacuum pumps to actually compress and stretch cells, which then helps them to actually express their different enzymes and different parts of that actually make them more replicable of what happens within humans. What I'm trying to do is actually use an electroactive polymer membrane, which is simply a membrane that I can actually wiggle using by applying an electric potential. So as you can see in the picture in the bottom left-hand corner, or right-hand corner here. So if I apply negative potential, it goes one way. If I apply a positive potential, it goes the other way. The chemistry for it is on the right, but I'm not a chemist. So yep, I'll just avoid that part as well. So the main kind of research I'm trying to do is trying to use these polymers and embed them into these tiny devices and hopefully create something that is either I can address, so addressable actuation is I can speak to whichever single kind of strip I want to speak to so they can all then actuate as I go along, or I can just actuate the entire model so it actually just creates nice little patterns as well. So the reason why that's all important is mechanical stimulus actually plays kind of an important role in replicating what actually happens in the human body. And hopefully by doing that, we can actually reduce the entire section. Does this have a point as well? We can hopefully reduce the entire section of 2 to 4, so this 2 to 4 years and this 1 year, to where we actually have a lot of testing being done on animals. We can actually reduce that by taking less time to do it, which is a more accurate model, and that should actually increase the amount of knowledge we have by this point to get drugs through quicker as well as cheaper as well. So in a nutshell, I'm trying to recreate organ function on tiny devices. I'm hoping to make them better models than the current models and trying to reduce animal testing as well. I'm using electronic signals to recreate those mechanical cues, and hopefully that should reduce the time taken for drug screening as well as the cost. Thank you for listening.
Thank you so much, Sanjay, and apologies for the technical issue earlier when you all heard me
no worries.
chasing up a catering order. Are there any questions at all? You presented that so beautifully.
Oh, thank you.
Look, they're done. There's one at the back. Thank you.
Hi, good afternoon. I was just wondering, how do you test the drugs? I'm guessing there are pores on it or something that help them go through, but how does that work, please? Thank you.
Let me see if I can go back to the slide. Yeah. So if you can see on this slide, there's basically 2 different channels, hopefully shown by the yellow and the blue. I'm colorblind clearly today. So the yellow and the blue are 2 different channels where you can actually input where the cells are actually placed onto, but you can also input different mediums onto those cells. So within those mediums, you can actually introduce your drug, and that way you can actually then test the effect it has on those cells by measuring what comes out at the other end.
Are there any other questions?
Thanks a lot. I came a bit late, probably I missed something.
Yeah.
So, you know our body, you always have the sympathetic, parasympathetic system fighting over.
Yeah.
So how will your system work with those natural
Lovely.
processes?
So I'm an electrical engineer, so I'm going to stick to the electrical engineering part of this. That's my excuse for everything. But so a lot of the other systems, so my system specifically focuses on trying to recreate the organ functions physically. Other systems within the world, so this is actually a commercial system now, so the Emulate system, sorry for advertising them, is actually trying to recreate the different microbiome, so introducing T cells, introducing different types of cells to actually recreate what is actually happening in the body as best as possible. So they are focusing more on the biological sides of it. So that's the best way to explain that, really. Yeah, I think there's.
Okay, I'm going to take 1, 2, 3, 4.
What?
And then we'll.
What happened to no questions?
How long are you looking to cut down the time of like the drug testing period to if this works successfully?
If it works successfully, I should hopefully reduce most of the wrong way. I should hopefully reduce most of the pharmacology steps down to probably 2 years, in essence. But that's provided it works, which is a big if.
How do you validate that the chips work as well as the organs that they're trying to mimic? And specifically, like, what metrics are you judging against?
So drug screening has existed for quite a while now. So any drug that you've kind of taken out, so simple ibuprofen, for example, has to be tested in the same kind of rigor. So how my system, to find out if my system works, I have other more commercial models as well as the actual current models such as animal tests or just the Petri dish tests, which I can actually just compare the results to and how closely that relates to actual inhuman tests as well for drugs that already exist and are already proven safe. That's the best way to measure it.
There are 2 more questions down here.
I just wanted to clarify something. So is the chip like going into someone?
No.
Oh, okay.
I was trying to make that clear at the start. Yeah, I get that question a lot, so yeah.
So what was the actual science behind the electroactive polymer? What does it rely on? Is it something similar to piezoelectricity or pyroelectricity?
Very similar to piezoelectricity. So the addition of an electrical signal causes the specific electroactive polymer I'm using is a conjugated polymer. Okay, I'm going to have to explain the chemistry, sorry. So the specific electroactive polymer I'm using is polypyrrole at the current moment, and basically it's a conjugated polymer with different junctions. And when those junctions are excited, they cause the ions around them to kind of swell towards them. And that, by that metric, they kind of then suffer, not suffer, they kind of experience something called hygroscopic swelling. So that they move the ions out of the solution into their structure or out of their structure depending on the potential that's applied, which causes them to swell depending on the potential that's applied. Any chemists want to disagree with me? I'll speak to you later. Oh, thank you.
I have one final question. What would be your advice to students wanting to pursue a PhD in your field?
Please do. So I think a lot of the people that I've spoken before have kind of mentioned it already. Find a community that you feel supports you in doing a PhD. So one of the only reasons I'm doing a PhD is my supervisor. So I did a smaller project for my final year master's project, which was kind of what introduced me to organ and chip. And she basically made me realize that I'm actually good at research. So if you have kind of that community that supports you to do research, please do. It worked out well in the end, as you can tell by all my cohort here as well, so yeah.
Thank you.
Thank you.
Welcome back, everybody. To introduce our keynote speaker, I'd like to introduce local London author Simon Hudson to come and give a small introduction on our speaker.
So good afternoon. Perry was a neighbour, is a neighbour, and also a gym buddy. And we got talking, and she mentioned the scholarship that Imperial was working on, a specific scholarship. And the conversation progressed where she discovered I was writing a book looking at the last 500 years of the black narrative on the world stage. From Africa, the Caribbean, North, Central, South America, the black presence in the Caribbean, in the UK, focusing heavily on Europe, as well as the black presence in places like Papua New Guinea, Tonga, and embracing the Aborigines of Australia. In the conversation, she said, "Do you know of any black engineers or scientists that we could associate with this scholarship?" And I gave them 4 or 5 names with a brief outline as to who these individuals were. My money, Dr. James West here, my money was on Elijah McCoy, but they chose Dr. James West. And I'm not saying they made the wrong decision, I'm just saying they chose Dr. James West. And the scholarship is now called the Dr. James West Scholarship. And I'm pleased to be able to present to you Dr. James West. Thank you very much.
Thank you for that introduction. And I was very interested in your introduction because it reads a lot on what I'm going to talk about. I chose to talk about black inductees into the National Inventors Hall of Fame because we're all familiar with halls of fame. Yeah, I'm sure there's a rugby hall of fame, a football hall of fame, basketball hall of fame, and so forth and so on. But none of them would exist if it were not for the National Inventors Hall of Fame. And the reason is that their ability to reach the audiences that they do depends a great deal on technology. And the National Inventors Hall of Fame has about 800 inductees throughout the world. It's not confined to the US. The requirements for induction into the National Inventors Hall of Fame is, first, you must have a US patent, but second, that patent must have changed the way people live, hopefully in all cases for the better. Now, if I were to ask the audience, based on that introduction, to think of someone who you might believe would be in the National Inventors Hall of Fame, it wouldn't take you long to come up with people like Alexander Graham Bell, who came from your continent, who invented the telephone, and you'd be absolutely correct. But now if I ask you a question in a little bit of a different way, can you name a black person who may be inducted into the National Inventors Hall of Fame? Many people would think very hard and long, but some of you would come up with George Washington Carver, who is well known throughout the world for his work on the sweet potato, peanuts, and so forth and so on. But he's inducted into the National Inventors Hall of Fame for teaching crop rotation to the South so that the topsoil wouldn't erode away as it did in the Midwest of the US. So if you got that one correct, what I want to talk about are other black inductees into the National Inventors Hall of Fame. And I start off with Granville T. Woods, who was a prolific inventor who had many, many inventions on things ranging from the design of the subway in New York City to a telephone transmitter, which he sold to Alexander Graham Bell. And it was the foundation for telecommunications, not only in the United States, but in many countries in Europe. This was the preferred microphone. And it lasted in telephony until I was inducted into the National Inventors Hall of Fame in 1999 for the Electret microphone, which replaced the carbon microphone. Now, we didn't invent the condenser microphone, but what we did was to make it practical by figuring out how to select materials with very deep traps that could trap either holes or electrons, and then to make use of the electrical field that's generated by the trapped charge. The condenser microphone was invented in 1917 by E.C. Wente, also of Bell Labs. And he was looking for a replacement for the carbon microphone back in 1917. And the reason is because the carbon microphone, although a good transmitter, also distorted the sound of the voice dramatically. And many people wanted to get rid of that distortion. And Wente thought that the condenser microphone would be ideal for that. And it is the most linear transducer even today. But it requires a battery of a few hundred volts in order to get for a change in capacitance as the air hits the diaphragm, changing the capacitance. But what you really want is a change in voltage. And so the battery is needed. And it was impossible at that time, and even now, for the wired system to support a voltage, high voltage, because of loss in the system, inductive losses, and so forth. What Sessler and I were able to do was to replace that battery with charges on a layer, a polymer layer that could trap charge and maintain that trap charge. And this made the microphone very simple, and not only very simple, but very inexpensive. I will never forget that in the Bell system, rejected initially the potential of the electret microphone because the learning curve had brought the cost of the carbon microphone down to around 60 cents. But today you can buy electret microphones with a FET built in for 10 cents a piece if you buy in large enough quantities. It's ideal sensor because it can be made in many sizes and shapes. It is particularly useful in hearing aids today. And since 2005, more than 2 billion electret microphones are made each year. Where do they all go? Well, they're in everything from toys to professional microphones. But enough about me. Let me talk about some of the other Black inductees into the National Inventors Hall of Fame. Marion Croak, who invented voice over the internet protocol, which is very heavily used today. So you see not only, and she was also from Bell Labs and a good friend. Moving on, Lincoln Hawkins. Lincoln Hawkins is a very interesting inventor. He learned to cure polyethylene so that it could be used to coat as sheathing on not only communications cables, but power cables. And it replaced lead. Just imagine if lead were still the preferred method of sheathing cables, how dangerous that would be. We would many more of us would suffer from lead poisoning. Link Hawkins was not only a chemist, but he was the first Black researcher at Bell Labs. He started in 1942. He's also the first Black member of the National Academy of Engineers. More importantly, to me at least, Link Hawkins was my mentor. And I want to point out right here that mentoring and mentees are a very important part of success in technology. So if you don't have a mentor, find one. If you're not mentoring someone, find someone that you can mentor, because this can be your lifeline, both up and down. So please take that into consideration. One thing about sports that one has to appreciate is that when Black athletes are admitted into leagues, and in this case, the National Baseball League in this country, Jackie Robinson was the first Black to be a member of a professional baseball team. And what I point out here is that sports seem to be the most liberal in terms of admitting people of color. But I just want to point out that in science and technology, Link Hawkins was a member of the technical staff at Bell Labs before Jackie Robinson broke into national baseball. Let's move on. Victor Lawrence, who received his PhD from Imperial College, is inducted into the National Inventors Hall for Signal Processing and Telecommunications. I cannot imagine what the world would be like without his inventions and contributions to the advancement. Well, we wouldn't be able to do what we're doing today. For me, from the United States, to be able to address you at your location. Victor Lawrence and I were invited by the U.S. Patent and Trademark Office to Tuskegee University, where we were able to take a picture next to the bust of George Washington Carver. There are 30 Black inductees into the National Inventors Hall of Fame. I'd like to discuss all of them, but that's not going to be possible within the time frame of that I'm allowed for this talk. So I want to encourage you, those that I do not talk about, to go to the National Inventors Hall of Fame website and learn about them. But I do want to highlight some of the very meaningful inventors, Black inventors. And Mark Dean, who I give credit for the personal computer, because he was able to create the peripherals that made personal computers possible. George Carruthers, for his ultraviolet electrograph camera. This camera is still sitting on the moon. I don't think it's operative, but his technology made it possible for some of the great pictures that we have of Earth at the very early stages of exploration of space. Patricia Bath, who invented laser cataract surgery, and she has a very interesting history in that she sold her intellectual property to a major company who put that technology on the shelf until the patent had expired. Then they basically repatented with some updates and claimed that they were the ones who invented the laser surgery, the use of lasers for cataract surgery. But we found out that she was the true inventor, or at least the National Inventors Hall of Fame found out that she was the true inventor of cataract surgery using lasers. Marshall Jones, who invented industrial lasers. These are lasers that can cut through inches of steel with ease. A very dynamic and useful tool for our modern industry. George Akon for X-ray spectroscopy. So you see the range of inventions are indeed very, very broad. Lloyd Hall for food process preservations, which allowed vegetables and fruit to be canned for use to be eaten out of season, because before his work, we could only enjoy those fruits and vegetables during the harvest or immediately after they were harvested. Andrew Beard for the Jennings coupler on railroad cars, which not only saved a lot of lives, but also saved a lot of time because saved a lot of lives because hand coupling of cars was a very dangerous occupation at that time. Otis Balkin for the electronic resistors, we use those throughout our electronics systems even today, and his inventions were quite a while ago because he was no longer with us in 1982. Emmett Chappell for bioluminescence in techniques, which is an extremely important contribution to the advancement of science. Cosworth for heating and ventilation. He, I think, was from one of the British colonies in Central America. Charles Drew for blood plasma preservation. Just imagine what life would be like without blood plasma, especially during exercises or serious injuries. Thomas Jennings for dry cleaning, dry sourcing, which is known as dry cleaning today. McHenry Jones for mobile refrigeration. So you see how these inventions accompany all of our forms of life. For Howard Jones for the conformal antennas, which is the technology that we still use today to communicate around the world. Percy Julian for cortisone. In its natural form, to make it is extremely expensive, so it was only available to the very rich, and he learned to synthesize cortisone and make it a very inexpensive drug and available to most people in the world. Louis Latimer, Thomas Edison is given credit for the incandescent lamp, But what Thomas Edison really invented was something like the flash bulb on your camera. It did not last long. It took Louis Latimer to learn to cure the tungsten filament to make the incandescent lamp light for a longer period of time. So the credit for the incandescent lamp should not go only to Thomas Edison, but also to Louis Latimer. Joseph Lee for the bread machine, Metzler for the shoelacing machine, Mills for improved methods for opening and closing elevators. As I understand it, it was a very dangerous part of the operation and required a human being to make sure that the door opened and closed properly. Well, he not only eliminated jobs, but he made it much safer. Gareth Morgan, who's given credit for many inventions, including the three-way traffic signal, but he was also well known for his gas mask. But not until there was an accident in a tunnel that was being dug under Lake Erie, which is near Cleveland, Ohio. There was an explosion that trapped about 40 people, workers in the tunnel. Well, Gareth Morgan and his brothers and whoever else he could find donned his gas mask and rescued the people in that tunnel. Well, he had trouble selling his gas mask before that operation, but after it, he was able to sell his gas mask without interruption. Rollet for automatic sugar refining. Taylor for microbiology, food safety, and testing. This is very important and keeps us from dying of food poisoning. It was very important from that standpoint. Elijah McCoy was an oiler on the railroad. He had a bucket of oil and a mop, and when the train was stopped, he went around to oil the bearings, and he and his father saved enough money for him for Elijah to go to school. Well, no school in this country, technical school in this country, would accept Elijah McCoy. So he went to England, where he earned a degree in engineering. Excuse me, came back to this country, presented his certificate to his boss on the railroad, and the boss gave him his oil can back. That would have meant that would have been devastating to a lot of us. And I'm sure that many people, when confronting that form of racism and discrimination, would give up, but not Elijah McCoy. You've heard the phrase, the real McCoy. Let me tell you how that came about. McCoy invented an automatic coupler that could oil the bearings on the train as the train was moving. This not only replaced him, but many other oilers whose occupation was the same as his. But the important point here is that others tried to copy what Elijah McCoy had invented, but people found that it didn't work as well as McCoy's invention. So when one wanted to purchase a automatic coupler, they wanted the real McCoy. And so that's how the phrase "the real McCoy" came about. What about the next generation? Because that's what I had as part of the topic of my talk. You're part of the next generation. But let me talk a little bit about what we did, especially at Bell Labs and other companies in this country. This is just a picture
Professor
of,
West,
yes.
I am so sorry, but we are running quite behind schedule. Is there any way you could wrap this up in the next 2 minutes?
Yes, I can.
Thank you so
Thank
much,
you.
Professor.
These are many people from that program are in prominent positions. The first African American assistant professor in the Fuqua School of Business and at Duke University. Cecilia Conrad is vice president and dean of Stedman Summer Professor of Economics at Stanford University. Lance Collins, who is now the professor and dean of mechanical engineering and department at Cornell. Let me go down. Sandra Johnson, who is responsible for the design of Deep Blue, the IBM chess playing. Sonia Hale, who was the first woman to be tenured professor at the California Institute of Technology. Gary May, who's chancellor at UC Davis. So this just gives you an idea that now the table is set. We have not only people who are trained to and have dedicated their career to training new people. I just want you to know that the foundation is there for you to be the next generation of contributors to the advancement of technology, and some of you to be inducted into the National Inventors Hall of Fame. Thank you very much. I'll entertain questions at this time.
Thank you so much for your presentation, Professor West. I'm just going to open up the floor. If there's anyone that has any questions, I'm just going to take this earpiece out because that's crazy. I'm just going to open the floor up to anyone that has any questions regarding past and present engineers that have paved the way for all of the people that are sitting in this room right now, or just any questions about Professor West's research, the work that he has done to widen participation for Black researchers in engineering as well. Okay.
Thank you so much, Professor West, for a very inspiring talk. There's no doubt that yourself and other people in the Hall of Fame like you must have passed through incredible challenges, but you were able to weather the storm and be able to become what you are today. So is there any advice you can give to young people that are aspiring to become global superstars like you? How would you advise them to handle the challenges that would make them drop their dreams?
Very, very tough question to answer, but let me try to see how close I can come to a coherent response, because there are many facets of this business. Even if you completely level the playing field for all participants, it is a tough job. As you know, I often say that there are two paths to success. Pay me now, pay me later. Many people who enter technology find it too challenging and other disciplines too easy compared to technology. So it is a lot of hard work, but as people of color, and especially people of color and women, there's another layer here that one must overcome. And that layer is race and sexism. because it indeed does exist in the world today, not only in the US and Britain, but throughout the world. This is a problem that we all face and have to tackle up front. One of the very interesting points is that I served on a committee for the National Academy of Science in the US, and what we found, I don't know, some of you may have experienced it, but in brainstorming situations, even though we all have the same background and same training, I always found that I did not go along with the majority being mainly white males. The interesting thing is that the solution was at neither node, but somewhere in between. So there's a difference in my thought process. Not only encompasses what I've learned, but it encompasses my total life as it does your total life. And so you think about problems or come up with solutions that are very different. Well, the National Academy of Science recognizes that the differences in people are extremely important from the standpoint of technology and the advancement of technology. It takes different backgrounds to come together to achieve the right and proper solution to a problem. So these are some of the important things. The other important aspect of survival is mentoring, and I can't stress that enough. Latch on to someone who's above you and have them help you up the ladder. At the same time, reach down for someone below you academically and help them through the process, because we all know there are good teachers and there are bad teachers. And we want to steer people to the right class. We want to give them support so that they can advance. I'm going to stop there. I could go on and on that question, but I'll stop there.
Do we have any other questions? Yes.
How long did it take from concept to completion to create your idea of the electric microphone?
Oh, the question was, how long did it take you from concept to completion to create your electric microphone?
Yeah, I heard them the first time, but
I'm so used to Zoom having a delay.
Trying to see if I could get my mind around that question, because in research, the order that you described does not exist. You poke nature and nature gives you a response. And that response is not seldom what you expect. In some cases it is. And so from concept to fruition is a very fuzzy line. And very hard to explain. And let me tell you why. I did not start out saying, let me invent a better microphone. I made a mistake and got lucky when it comes right down to it. Yes. And I'll make this as short as I possibly can, but when I joined Bell Labs as an intern, a group of psychoacousticians were trying to measure the intraoral time delay. This is, if I give you a sharp click, what's the distance between that and a second click before you hear two click? It turns out that the integration time of the ear is about 15 milliseconds. They were using condenser microphones as headphones, and people couldn't hear the results. And I was asked to see if I could do something about it. Well, I found a paper in German that described a solid dielectric headphone, made them, everything worked well for about 6 months, and the microphones and the headphones were dying, just losing sensitivity. And I took this thing had a 500-volt battery in it. I took the battery out and the leads fell connected between the oscillator and the headphones, and they sang beautifully. Why did they do this? Well, it's a capacitor, it stores charge, so I short-circuited it and tried it again, and it still worked. And this led me to discover electrets. The electrets had been around since, Heaviside in the 1700s, who's also from England, had a lifetime of 6 months. So they had made electret microphones, but their lifetime was only 6 months. Well, this is when I teamed up with Gerhard Sessler and we began to ask the questions, can we improve on this technology? Can we find different methods? Now, before that, they were orienting dipoles in the material and using the external field from the alignment of the dipoles. What Sessler and I did was to find materials with deep traps where we could jam an electron in and close that trap. And that electron is very unhappy because it wants to be free to combine with the hole. So its electrical field is permanent, which is what we needed for the condenser microphone to work. And so therefore the battery got replaced by a thin sheet of polymer. So it's a long roundabout way of answering your questions, but I wish it were as simple as I have an idea and making it work. It didn't work that way for me. It required a lot of other support and help.
Thank you. If you could go back through all your experiences, is there anything you would change and why?
Yeah, but I have to go way back. I have to go back to where I, and growing up, my brother and I were, from the time we were able to understand English, were my son the doctor, or lawyer, or teacher, or preacher, because those were the only 4 occupations, professional occupations that were open to Black people at that time in this country, in the United States. And I didn't want to be any of those. Technology and physics were far more important to me than the biological sciences. What I would have done differently, or what, if anything could have been done differently, it would have been to be more accepted at that point that technology was an opportunity for me to grow. Now, the impediments that existed in my time are a little bit different today. Today, we're discouraged from technology because in many cases, people still do not believe that people of color have the same mental power that white people do. And so if I could change anything, I would change that paradigm for everybody so that we all had a level playing field. I think if that had been the case, my career may have been different. I'm not sure how it would have been different. I'm not even sure that I would have been more proud of what I had accomplished than what I've been able to accomplish so far. Because crystal balls lie. They don't tell you the truth. And this is the reason that I cannot say whether this would have improved my ability or not, but I would have loved to have had the opportunity. What I am now doing is making sure that you have that opportunity, that people look to you as their equal when it comes to technology and the advancement and contributions to technology.
So we have time for one Oh gosh. Okay, so we're going to have two questions, one from this lady here and then one from Simon Hudson, and then we will wrap things up with Professor West. One sec.
You talked about like commonly like being the only person of color among a lot of white people when you're working. I was just wondering how you've like tackled racism and discrimination throughout your professional life.
First of all, I don't believe I'm inferior. First of all, I think that I'm equal. Second, I don't back down. By backing down, I mean exactly that. If I have an opinion, if I think a certain way about a problem, even though it may not be in agreement with my counterpart or who I'm discussing, I stick to my guns. So those are two aspects of what's important. And again, I can't think of any others that would be more important, nor can I think of, look, we all develop techniques and shields to shield ourselves against racism. We all develop means of defending ourselves against racism. And as long as we do those two things, at least when I have applied those two principles, the playing field does seem to be a little more level, and that my opportunities are approaching equality.
So thank you for that answer there, Dr. West. In the 70s, I believe you formed the Association of Black Laboratory Engineer Employees, ABLE. Did you find that successful, and is ABLE still in existence?
The answer in reverse is that ABLE still exists. In fact, about a month ago, I gave a talk to the group at Nokia, which is still called ABLE. We organized the Association of Black Laboratory Employees to improve the quality of life for everyone at Bell Labs at that time. And we did because the employees, Black employees at Bell Labs were heavily loaded in the services area, to keep the grass cut, to serve the food, to chauffeur the limousines, and very few of us were in the technical ranks. Although I must say that I chose Bell Labs as a place to work because I found people that looked like me that I wanted to be like when I grew up. But more importantly, we wanted to improve the quality of life for those of us in technology. Did racism exist at Bell Labs? Of course it did, because it exists everywhere. But the one thing that is true in technology that is seldom true in other professions is that you are evaluated based on what you contribute. And so truth is true, no matter how you look at it or where it comes from. And so the freedom that this gave technology, we wanted to transfer that throughout the system. And so doing, ABLE created the program, called the Corporate Research Fellowship Program, which funded and mentored more than 500 women and underrepresented minorities toward PhDs in the physical sciences. So the purpose of the organization, some of the purposes were fulfilled in improving diversity in engineering and technology, but also in the management sciences. We also were able to get a number of Black people promoted in the services area. So ABLE was a very successful Black organization. It did many, many things other than what I've mentioned so far, but those are the highlights in technology.
So, Professor West, from everyone here at Black to the Future, from me and the organising committee, and also the committee of the James West Scholarships team, thank you for everything you have done to move forward Black engineering research in general, and also just for being here with us today, for imparting your knowledge, and for everything that you have done. Thank you so much. If we can give...
Thank you. Bye.
Right, we are running a little behind schedule. Apologies for that, but we are going to race on right through to our next speaker. We are going to have Dr. Ernest, who is going to come and give us a talk now. We are now in our session, which is engineering in academia and in industrial research as well. Thank you so much. Oh, yeah, you can check on your...
It's always tough to speak after great people. So hopefully we have been in the blue sky, and I will try to bring us down on earth. Something I remember in the last one, he says, the foundation is there for you to be successful. And that's actually what those kind of projects are trying to create. So we have the foundation to success. So my name is Ernest Kamavwako, and I work for King's College London. I'm a researcher. So a bit of my life, just one chapter, or one section maybe. So I chose the title Fluid Intake Monitoring because I will be discussing two of the projects in my lab, and then one of them is fluid intake monitoring. And so I am originally from Congo. I went to Denmark for studies, and then when I started, in my cohort in the engineering department, I think we were 100-something, and I was the only Black student. And what made it a bit more challenging is that I came from a French-speaking country, learning Danish to study in Denmark. And then I discovered, although lectures were in Danish, all the books were in English. So I had to study. We didn't have Google at the time. You know, you couldn't just Google it, translate. I had my French to Danish dictionary, Danish to French, French to English, and I still have my book from year one. I don't sell them because you will see so many words on the line because I had to search for them. While my student mates will spend 2 hours studying, I will spend probably 6 hours. And that was the challenge. And then performing better and better. At the end, I did my undergraduate, and then I got a PhD in biomedical engineering, focusing more on systems and signal processing. And after that, I said, okay, it was tough to do a PhD. Maybe when I became a senior level, things become easier. No way. After that, you have to prove yourself. You become a lecturer, then senior lecturer, then now I just got my promotion as reader, and then we keep on going down. And I'm also guest professor at the University of Kindu in Congo. That makes it a bit of easy for me to touch base all the time, because some of my research is focusing on low-income settings. So today, I am also head of Bioengineering and Sensor. This is my lab. And then I will talk about two main research projects. I wrote in three because one of them is just a EDA project we're running now. It's called Success for Black Engineers. We got funding from the Royal Academy of Engineering to promote the success of black engineers, not just our own students at King's College, also trying to reach out to those who are A-level and GCSE. What I found out also with my own private life is that we have this culture barrier sometimes, especially parents who are from Africa. We still have this idea of you have to be a doctor, you have to be a lawyer, you have to be a politician to be successful. And no one tells you to be an engineer. So what we are going to do is now, if we reach out to kids or children in secondary school, then trying to provide this motivation of why you want to become an engineer, inviting them at King's. But for our own black students, what we are trying is to minimize the academic gap, at the same time trying to provide them mentoring. So I am in charge of the work package that takes care of academic mentoring, at the same time peer mentoring, to make it much more easier to collaborate, as to learn from those who are at the senior stage. So this is what we're working on, and then the project is ongoing, and hopefully we will have more. So the idea is the UK black population is about 3.5, I believe. In London, we are over 10%. But then if you look at our faculty, for example, you only have 4% of black. So what we are trying to see, can we reach those 11% at the London University? So that's my EDA contribution at my university. Now, one of the projects I want to discuss is a wearable device for murmur. Murmur comes from the sound of your heart. And when your heart beats normally, you have very specific patterns. And when there is something wrong, then you will have murmurs. Those are bad sounds. And then doctors, when they listen to babies, they want to quantify, is the baby okay or not? So you have almost 9 out of 1,000 baby born with heart defect. And then someone will say, okay, why bother using a wearable device for detection while we have echo or the stuff? Yes, we do have echo, and the NHS spent a lot of money for that. Out of those 9 children out of 1,000, you also have a lot of false positive. We spend money for nothing. But the key point is also to look at low-income settings, because what we do in many countries now, it's common. You have a baby, they will check everything before you go out. In some countries, even in high-income countries, you still have to wait for those GP consultations before they discover. And the reason why I went into this one, my own son was born with a hole in the heart. Although we went to all the GP sessions, call it GP appointment, when they are 3, 5 months, 1 year, it never detected the disease. And that's what happened. Many of new GPs are not well trained to diagnose from heart sound. It's only when he became 2 years, we went to the US during my PhD, he got sick, just, flu. But in the US, they are careful, they will check everything. Then they asked me if I knew my son had a murmur. I said, no, I didn't know that. They said, oh, he had one. And they do echo, they found a hole in the heart, and then by the age of 6, they had to do open heart surgery. But in many countries, you see people have to travel miles for checkups. And then if you travel 100 miles and then nothing is wrong with your son, you have to come back. But if you can have a system that is low cost, that may give you a probability of having a disease, then you're at least traveling for a reason. The idea is quite simple. On the top, you have a healthy heart sound. You have a specific patterns beating of the heart. At the bottom, you have some kind of unhealthy murmur. It could be just noise to your channel, so you have to construct your algorithm to specifically detect those murmurs. And of course, provide the probability of the person having a disease. At the moment, we are focusing on children, but we have not just started collaboration with Heart Valve Association, Heart Valve Voice Association, where we're going to look at also grown-ups with valve problems. A valve is a mechanical system that helps the heart pump blood in different parts of in the heart. So we did present our algorithm to the PhysioNet Challenge last year, and then my PhD student, Bo, who's here, is now my postdoc. They, with his student mates, they made an algorithm, and then they actually won the first prize. So we're now trying to build more into the algorithm to increase not just the sensitivity, but also the specificity of the algorithm, because we don't want to send it somewhere, then it's worse when you're healthy than we tell you're unhealthy, because then it makes matter much worse. So then if you want more about the paper, we have a paper out there. It's a conference paper where we describe the algorithm. There's no IP, no patents. We just want to share it as an open source algorithm for other people to use it and to improve it. So that's what I do in terms of wearables for heart disease. And because I'm a bioengineer, I'm focusing on biosignals and sensors. Another part of my research is actually how to monitor fluid intake. It seems quite banal, quite vague. I can just drink. But when we get older, we actually lose sensation of thirst, and we drink less. Because we also lose muscles, the water distribution in the body decreases. So we don't really sense a lot. So hydration is important. If you want to age healthy, you need to drink. You need to eat well. Now we talk about varying your food, but we focus mostly on drinking. Older adults, because of those loss of sensation, diminished thirst sensation, because of loss of muscle tissues, they tend to have more drugs because of different disease. They actually are susceptible to dehydration. And with dehydration, the NHS spend over $1 billion a year just for hospitalization. And when you are also dehydrated, there is a risk for longer hospitalization, increased medical costs for the NHS. In many cases, you are more prone to death than those who are hydrated properly. Why do we care? This is how the world is changing. In many developed countries, in about 30 years now, the ratio between people who are 60 and over and below will be 2 to 1. That means the number of people to take care of our parent or ourselves when we get there will be low. Therefore, technology is important in terms of taking care of other people. But the way it's done, you have the pressure in the NHS, and then they try to push all the carers to actually measure how much they drink and how much they output. And this is usually what happens. You have a flu chart, and then if someone is okay, they can fill themselves up, or you need a carer or a relative to try to follow up and then noting down. And if you look at statistics now, many of those fluid charts are not properly completed. It's hard for clinicians to actually sometimes adjust the medicine because they don't really get a good picture of how much they drink. There are a lot of technologies out there that are used for trying to detect human actions, to detect fluid intake, from cameras, for different sensors as well. And we just published one paper in Sensors where we looked at a review of what are the technologies that are using cameras for fluid intake monitoring. But if you look at now how the process of drinking is done, is that you need to go take the container, put it to your mouth, and you need to swallow. It's only until you have swallowed it, you can be sure that you are drinking. Because you can give someone a cup of water, you ask them to drink, then they put it over into a sink. And if you use a container or a cup to measure how much they drink, the cup will measure how often you empty the container. And if they don't like to drink, it's easy. You turn your back, then they just put it there. There's nothing to do. So what we are trying to do is, can we then try to look at not just the technology which is external, as well as looking at physiological mechanisms. Therefore, our engineering problem to this is defined as a detection of the intake actions. Can we classify between drinking, eating, and other? Because if I swallow my own saliva, it's not fluid. So it's something I'm reusing. And we swallow our own saliva many times a day. And therefore, if you only quantify swallowing, you may start counting saliva as fluid. And then, of course, try to estimate the daily fluid. And our idea is to construct a kind of necklace device where you can have different sensors on top of it. I have a couple of PhD students who are working in different components of this problem. One of them is Xin. She's from China. She's looking more into the detection of the action using cameras. And then I have one, I think she's defending this Friday, so she has a Viva this Friday. She's looking more into how do we distinguish between saliva, drinking, and solid food. And then Iman, I think she's here as well, she's more looking into how do we quantify the volume that is being intaken. All of that, our setup in the lab is quite easy. We have different cameras, external one and the one that the person is wearing to face up. And then you also add more other sensors. One of them is the EMG. The EMG is the electrical manifestation of the muscle. If I move my muscle, before the mechanical movement, the brain will send electrical activities and I can record that. That is called EMG. When we swallow, there's a sound coming because the bolus makes a mechanical movement. And using a microphone, you can listen and record the sound. At the same time, when you have a camera facing up, you can then detect the movement of an object that is actually coming close to your mouth. But then if an object comes closer, is it really a drinking or just something? Then I will put it away outside the camera view. Trying to combine all those three technologies to try to see, can we then make it better in quantifying fluid intake? Quite a small problem in advance, but now it's becoming different branches of research. And one of my colleagues at King's College, she's more interested in using the same system to quantify swallowing disorders for people who have dysphagia, for example. They can't swallow after stroke or after a motor neuron disease, for example. Just a bit of results. So far, we are actually quite good in differentiating between the drinking and drinking of water versus saliva, with a quite high sensitivity of 96%, so that you are sure that with 96%, when I swallow something, just measuring the biomechanics from the EMG and sound, I can almost know if it's water or fluid or it's saliva. The next step now is, okay, how is the biomechanics of swallowing fluid versus solid? So we have an ongoing investigation. A paper is being prepared where you have a low sensitivity, around 82%, because the mechanics is almost the same. And what you're trying to do now, can we then improve? Because we don't want to count eating as swallowing. With a camera then, you can add an extra layer. Is the person using a fork, using a spoon? Can you detect, is it a container or just a bag of chips? That may give you an extra layer of information to know if it's eating. Or you can measure chewing, for example. Is there any chewing movement prior to swallowing that may tell us something about if the person is drinking or eating? So that actually, this is my team. You have seen them, Carlotta, Iman, Shin, and Bo. And I also work in one aspect of research where I do more robotics view of using muscles, electrical activities to control prosthetic hands. With the time I got, I didn't want to present that, but happy to discuss if you're interested in prosthetic control and so on. Say that, thank you.
Just wanted to open up the floor for questions. Right, we've got a couple at the back here. Just going to take two because we are running a little behind schedule. Sorry, what was the...
You said you run a lab. So what are the intricacies of running a lab?
Sorry?
You said you run a lab and you have different PhD students that work in your lab. What are the different intricacies when running a lab? Intricacies, like the different things that it involves when you run a lab.
So, to run a lab first, you need money. That's the first thing. And then usually you set up, when I got to King's College 5-6 years ago, I got what we call a startup fund to take care of the basic, the first tools you need for your lab. And then after on, some of them will be obsolete because you have new technology coming. So you need to keep up applying for fundings. At the same time, being able to train people who join your lab. So those are the key thing of running a lab. So if there's no money, it's hard because then you keep using the same device, and you need a very nice way of training and inviting people. I'm lucky enough that I get interest in many students trying to do internship in my lab. I have simple devices, but those are quite high tech and state of the art.
You spoke about the impacts of fluid intake on aging people, but how much does fluid intake impact young people like us? And how much can it improve cognitive ability if I drink more water?
So, when you are younger, your body is over 65% water. So when you lose a tiny amount of water, you don't really feel it much because you have enough reserve. So hydration is important for everyone. If you don't drink enough, your cells don't function properly. The main difference between being young and being old is the likelihood of being dehydrated. And if you are dehydrated as in older people, the damage is much higher also because of their lifestyle. Usually they don't move a lot. They take lots of medicine, but as younger people, already if we take the medicine part that we don't take as much as older people, when you start have the acute phase of the dehydration, you can easily actually mitigate for that compared to someone who is getting at the acute phase at the same time as less sensation of thirst. So they can't really feel, I need to drink now. But while as younger, when I start feeling, oh, today I haven't got enough, then we can drink. But what we are hoping the system is to work as an alarm system, for example. Myself, sometimes when I sit in the office, if I don't have my bottle in front of me, I forget to drink. I will keep on writing, having meetings, then I'll say, oh, today I didn't drink enough. But once I have my bottle of me, when I look at my phone, I have my water and I can have a sip. So it's important for everyone. Our body needs water, needs fluid, because it's made of water.
Thank you so much, Dr. Ennis, for your presentation today. Give another round of applause. Thank you. So our final presentation is from, no pressure, it's from Dr. Christelle Mavina. Thank you so much for agreeing to give a talk with us. She works at PerkinElmer, and she's going to give a talk on engineering in industry. Thank you, Christelle.
I'm going to make it not too sciencey, because even I'm tired too, but more towards the challenges as being a black female going through my career until now. So I hope you'll see the challenges and how I overcame them, and how, if you have experience in how you can overcome them. So I'm French, born in Paris, lived in the Congo, Brazzaville, moved to UK, I was 12, so first was language barrier, so I had to learn the language. My mother literally sent me into an English school and like, right, go. So I just said dictionary, French dictionary, everywhere, just go learn. As a young girl, I was always interested in sciences anyway, so it was the thing I wanted to do at school. I was always good at science and maths and physics, and so I just carried on through that. And through the schools, I think, French and UK, you don't actually see much racism, differences, and sexism through that learning stage. Everyone's going through the same process. It's quite thorough, to the point you get to your A-level and university. So I'm just giving you a little example of, where I was born, where I've gone and eat. So I would say the first challenge was actually after my A-levels. So A-levels, I did well, all A's. I was a, A star, whatever. but again, I applied to all universities, just like you do, everyone. Imperial, Cambridge. I think I even went as far as Warwick and all universities because you can. At the time, actually, you still do phone interviews, by the way. So I did quite a few phone interviews. And a lot of the professors, and you know your science, you speak well, oh, very well. And then when you came to some of the face-to-face, that was interesting. So one of the first face-to-face, I won't name the university. So you go there, you're all suited, booted. You're like, yes, first university. You go to the interview. Gentleman comes out. It's like, Miss Mafina. So I get up, and first thing he says was, And I was like, okay, believe you me, it's a room with other, interviewees. He's like, I wasn't expecting, Mafina sounds more Italian. Okay, so thanks. Already I was like feeling down, so okay, fine, never mind. So you go into the room, we talk science. So I was thinking, you know what, let's talk science. Nothing can go wrong when you talk science. Wrong. It's like, so where are you from originally? French? No, originally French. Originally French. Like, why does it matter that I say Congo, Nigeria? No, but he wanted to. So I was like, fine, I'm from the Congo. Oh, yeah, I've seen your kind. Oh. Okay. Now, being one of the first interview, you first go, you know what? It's ignorance. I'll let it ride. Carry on the interview. Went well, go back, you go to another interview. But it sticks, You go back home, and I was like, Mom, the interview went well, but so-and-so did that. Mom was furious. Was like, what? This is not right. I'll come with you to the next interview. I was like, oh, okay. Next university interview. Again, won't name the university. So you go there. Again, everything's fine, da-da-da-da. Miss Mafina. So I'm going to get up. And I was like, And I was like, oh, God, this time my mother's sitting next to me. And this gentleman goes, I thought your name would be more African. Now, again, mother sitting next to me. She lost all color. I just went, it's okay. Went in there, did the interview, talk science, showed it up, come back. And when we came back, Mom was like, you are not studying here. I was like, okay. So those are the challenges that I kind of faced during that. And that was just, we're talking 2002, 2003, right? So ignore those two universities. Despite their name, I was like, whatever, there's other university, find the right one. Was a blast. So did my master's in science at Queen Mary University, applied chemistry, so basically all chemistries you can think of, organic, physical, forensic. And that's where I really learned that I'm more of a material chemist. I'm more into the inorganic chemistry during that time. And again, it was very fun. Once you're in there, being female, being black, in a master's setting, it was actually 50-50, both women, the culture and everything. So there's not much racism. And if you do, it's usually because there's that old lecturer somewhere who hasn't come out of his office in 25 years or gone into the lab. He comes into the lab one day, asks for a syringe, and you go, and you're like, okay, great, then. Once in a while. And then, so that was, I think, one of the challenges for sure during my A-level to master's as a black female with a name that's not, apparently, as not African as it should be. So that actually was quite challenging, because, you go through there, you feel hurt, because you go, okay, great, so you liked me on the phone. I don't think you realized who I was on the phone. Maybe my phone voice is very white. Who knows? I don't know. I don't hear myself. And then, and then you go, okay, that's fine. You know what? I went through this. It's fine. I got the master's. I'm into the class. Let's just move on. So you just go along with it and you move on. Then I went into a PhD. So that was really fun. I went through the SWAN program in Queen Mary, where they try to advocate more female into sciences. So through them, so you've got here actually my mom and Dr. Karen, my supervisor, they were meeting, they were friends, they're still friends. And, through them we went through conferences and you do your PhD. So this time I went from applied chemistry MSci to a biomed PhD, because I thought that if I went into chemistry, I was like, I just done chemistry. I want to use that chemistry and do something else with it. And so they were like, oh, what about biomed? It's a bit of chemistry, and then you learn a little bit on the bio side. I was like, okay, why not? Okay, I'll try it. And indeed, it was fun. So it was all about bone repair. So I was actually making fake bone, like synthetic bone. So for about 4 years, people thought I was making a Terminator, so that was quite fun. Especially at that time, I remember there's a satellite called Skynet that went out as well. So it was brilliant. But again, you go through life, PhD-wise, I think most of the challenges were, again, talking with the technical support. Again, back then, you still had the older generation of technical support, like, what do you know? What do you do? How do you use the instrument? Oh yeah, I know how to use the instrument. I've been trained. Are you sure? Oh, but you seem weak. I'm going to test our stress. I'm like, I can do it. So you still got that a little bit, which unfortunately followed me through to my next role, which is experimental officer. Again, same Queen Mary, this time, same school, so the School of Engineering and Material Science. So there, by that point, PhDs in the pocket. I've actually applied for a TA role in the meantime while I was writing, so I was doing supports with teaching and students, mentoring. As Jim West said, is important. Mentoring is important. I still mentor at least 2 students per year, and I think that's really nice because you pull them back up, and it's nice to help out. And during the experimental officer role, I think it started quite bang on for me in the sense that the university just got a lot of funding for a new lab. So I had to organize the whole lab from scratch. The electricity, the gas inlet, name it. It was just, you open the door, there was just nothing. So I was like, oh, this is brilliant. It'll be really good for my CV, and and that means I'll have to coordinate with facility. Brilliant. However, black, female, young, you go into the health and safety meeting, and then you're like, oh dear, okay. Oh yeah, no, we want the instrument machine here. Rah, rah, rah. I was like, we're on the 2nd floor, so it can't go. I was like, why? The instrument weighs X tons, you need X amount, there's no power supply going up there. Oh, what do you know? We need a 3-phase plug, and you have to explain yourself. I almost had to debate with everyone again. And I'm pretty sure the first year I felt like I was defending every decision I was making because I was the youngest in the team. I was female. Did the black work into it? Maybe, maybe not, I'm not sure. But, considering the other 2, you might as well add that on. I was like, yeah, might as well. But again, it was a bit of a struggle trying to get everyone to listen to me because they're like, oh, she's the young one. I'm like, yes, but I got hired for my skills. I got hired because I know. And then after that, the lab got set up. I think we had about a year and a half to set the lab and get the lab working, running for the coming students. Getting in touch to the technical staff, the facility staff, talking with gas, electric, and so on. And that did all that organization, talk it through. And I do remember that the first year was always defend. But then I was trying to do this with patience. I was trying to not get angry a lot of the time. I was like, you know what, Christelle, just do it. They'll eventually get it. And hopefully, if it gets set up, they'll see the lab work. It's golden. And that's what it is. It was literally through sheer patience that I was like, and sheer, like, I know what I'm doing. And when I did, I was always like, here's my bullet point, here's my reason why. I'm not just saying, do it because I said so, but I said, here's why we can't do this here, here's why we can't do that here. So a lot of the time, it was always defend, and a lot of patience. But eventually they were like, you know what, this girl knows what she's doing, the lab is working well, the students are loving her, all the lecturers are like, woohoo, the labs are working, they're clean. And I ran that lab like clock for about 3.5 years. It was fun, and it was a mixture because I get to teach in the lab, I also did lectures. I got to use all the instruments as I wanted in the lab, so I had the time to do some sub-projects on my own. Managed to write so much collaboration with everyone that came in. I think I've published in 10 collaborative papers or something like that, just through the work that I've done through this lab, and actually still ongoing to this role. So during the experimental officer role, well, I also didn't like, and actually you can see the comment there, where the older generation, like, they're like, oh, Christelle's in the cake, whatever, and you have to call him uncle. I'm like, why? My family. It's like, okay. So there is still that thing, like, young women, let us protect. I'm like, no, I come to this job to do the job. I'm not your sister, I'm not your cousin, I'm not your, no, like, you and me, colleagues, I'm not, whatever. So again, it's through a lot of patience. You have to just go, hi, Jim. Oh, Christelle, no, it's just Jim, it's just Christelle. It's not, you have, it's repetitive, and it's a shame, and I think we still need to do it, but it'd be nice to not have to do it. And then through that, as I said, I was charged of so many instruments, and I actually got trained through all these supplier instruments. So my CV was starting to look really nice, so much nicer that PerkinElmer, the people I work for now, were like, ooh, this girl, she knows her stuff, like, let's grab her. And the other reason is because of all the hard work, I managed to get the lab accredited so we can get other universities and other small schools who don't have the instrument to pay a small fee to use their instrument to run some samples. So I kind of pissed off the local sales representation in London because they would go to a university and go, oh, do you want to buy infrared? They're like, no, man, we'll have Christelle run it. And it was like for about a year, like, who's Christelle? And eventually they caught on me. They caught and found me. And actually it's really funny because I believe one of the sales reps wanted to talk to me. I think it was back in, I think at that time it must have been like July or something, and I was like, no, I don't have time because I'm setting up labs. I just don't have time. So, oh, Christelle, this sales lab's coming. I was like, I don't have time. I don't have money. I don't have time. And then the only way he got in is because one day we invited a few other suppliers because we were running a small industrial placement. So he came with his field science associate, because I didn't want the sales guys, I just wanted the experts. But he was like snuck in. And he's like, by the way, how about working for PerkinElmer? I'm like, I was like, what do you offer? And he's like, well, we can maybe 10K more on your salary and you get to travel the world. I was like, oh, okay. Let's have a chat, shall we? I was like, oh, this is getting interesting. And lo and behold, I took the job. And I did get to travel. So my first role as a field application scientist was literally to do what I'm doing at uni, but did it worldwide. So I trained students, customers, or anyone who pay for my services. I wasn't cheap. And actually did the present training, so of sample preparation all the way to data interpretation. And because I speak French, I did it all in the French Africas. My Italian is okay, so I did it as well in Italy. And those regions you see in the map is literally where I was sent for about 2-3 years of my life, which was quite funny because when my mum used to try to call me, she'd be like, "Where are you? Before the hour are you?" And then I was like, "Yeah, I'm in Slovenia, or I'm in Kosovo." But however, those, although fun, that also bring a different side of the challenge again. So as a credited scientist, by that point, I'm a chartered scientist, I'm a chartered engineer. I've got 3 years in the bag of experience. But there's always a but. You get sent to, for example, I think I had to go to Saudi Arabia. It's fun. The people there were brilliant. The training went super well. The bureaucracy for it, as a, at the time, Black Christian single woman, was atrocious. So my colleague was supposed to go in January. He broke his neck, or no, not neck, he broke his leg. He broke his leg for Christmas during skiing exercise. So then they go, "Oh, look, we have another expert. We can send her straight away. But here she is, you know, it's Christelle, blah, 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 blah." They go, "Oh, that's lovely, but we don't have facilities for women, so we'll have to prepare facilities for her in Saudi." I was like, "Okay, fine." But then throughout that process, they asked of me my master's certificate, my PhD certificate, my chartership certificate, because they wanted to really know if I was the expert. My colleague, a man, white, just his name, just his card, done. They were like, "Oh, we need this for Christelle and this for Christelle." So training was supposed to happen in January. I didn't go till May. Why? Because of the paperwork. Everything had to be stamped, blank, stamp, stamp, stamp. So I was like, oh God, that is one challenge. And you will see that this was very hard. I was just like, this is not great. And that was not just Black, that's just because you're female. Like, you had to prove your expertise in that challenge. I went there, the training went well, the people were nice, you had to be escorted everywhere because, you know, I was single woman in Saudi. And that's really the extreme, all right? I'm not saying in every country you travel will be there, but there's definitely been other experiences like that where, again, I've been sent to Kosovo, really nice country, lovely people, Black, Christian, female, but it went well. I'm fine, you see, I'm here. But it's a challenge. So I think as a Black person, and also as a Black female, there are some challenges, but the idea is you're allowed to be upset. I was upset, like, you're allowed. I was like, what? That is not fair. Why do I have to wait 3 months to get there? But you go out, you know what, let me just send the paperwork. Let me just be patient. Let me be calm. Let's just deal with it and go. It went well. The training went well. They actually asked me to come back and I was like, no. So as a Black female engineer, I think there's still challenges. It'd be nice if there isn't, but there are. But I really do strongly recommend that patience is important. You're allowed to be angry. I mean, I think the one with the interview, I cried I went home, I cried, and I was like, yeah, move on, carry on. But it's just the next steps, like, you know what, I'll forgive you, let's move on. Because if I had carried on that hate, I don't think I would have taken a job, or I don't think I would have done this. So, yes, it's important to take it in, just be patient. And I think in terms of my career anyways, it's if you do the work and you prove yourself diligently, you'll eventually get to a point where Black, white, hopefully, female, male, doesn't really make a difference. But that is my experience as a Black engineer working in industry now. Working on.
Thank you so much, Christelle. Can I just say, I've known you half my life and there wasn't a single picture of either one of us together in that presentation. Shocking.
No, I think there's a picture of Viv, yeah?
Yes, but not me.
I'm sorry. I'm sorry. I'll find one next time.
Do we have any questions for Christelle before we wrap up today? Any questions about what it's like working in industry and not in academia? Yes.
Thank you, Crystal. That was an excellent talk. Really enjoyed the stories. I'm Wayne Mitchell, by the way. What I was going to ask is, throughout you often spoke about throughout your journey that being a black, female, Christian, those three intersecting characteristics, they seem to have an impact. How do you overcome the fact that you can't change who you are in those situations, but yet they seem to always keep impacting? What do you do?
Usually you just, it depends on the situation. It's either I ignore. I'm like, oh, the person speaks and you just go, I shall kill you. I'm having an Ali McBeal moment, And then you just try to zone it in and you know what, it's okay. Most of the time it's in a science context, so I just overwhelm them with the science. I'm like, ignore me, just listen to my science. And then usually the conversation goes that way, and then it gets shoved a little bit on the side. So it's more the patience, like reining, because getting angry doesn't work. I've tried it before, and sometimes you do. You get that one person that just pressed the wrong button, right? And you do your effing this and effing that, but most of the time I'm just like, it's okay, Christelle, you know what? You go home tonight, you're gonna see your dog, you're gonna see your husband, you're gonna have a nice meal. You try to think of a happy space, and then just finish and just overwhelm with a science question or try to answer them with a science. Finish that conversation. Thank you very much. Have a good day. Bye. And then usually, if I don't have to deal with this person again, brilliant. If I do, I just try to stay civil, and you just stay on the technical, scientific side, because there's no point going personal. They're just going to be trying to press. So it's managing that.
Fantastic, thank you.
Yeah.
Yeah, I think I always go back to family.
Yeah.
So what you experience, especially for many black girls, is like sometimes parents will be a barrier for them to go for engineering studies. How was it for you? How was the support from the family?
My family, half my family are scientists or accountants. So my mother was like, what do you want to do? Okay, go. What do you want to do? Okay, go. But I think it was just a family thing, just because I'm not saying not all black family are, but I think some of the black families may not have my mom went to university, her dad went to university, so we've had 2 or 3 generations of university educated elders, and so I think that kind of helped as well. So when we grew up, they were like, oh, what do you want to do? Even if you said you wanted to be a vet, they'd be like, do what you want. If you think you can do it, do what you want. There was no family
So what
pressure.
advice would you give to young women, girls who are struggling to go to engineering because parents...
Find a mentor. Find a mentor. I mentor twice. I mean, when I can, because obviously being a product manager now, I have time, but I don't have all the time in the world. But finding a mentor helps. Like Karin, she was my mentor. I think my own mother was my mentor because she was really supportive on everything. If you find that one person that tells you, you know what, you can do it. It's, oh, but it's difficult. No, you can do it. That tiny, close person, that makes quite a lot of difference. But finding a mentor if she can. And it doesn't have to be at uni. Right now, I am registered as a mentor, I think, at Queen Mary University, but it's an open forum. I have some students who've met me through conferences like this one, and they talk to me through LinkedIn. I don't mind. I've got 10 minutes on LinkedIn. I can. If I can find the time, I will. But finding a mentor, I think, really, really does wonders.
Do we have any other questions? It's the final question.
Hi, thank you very much for your presentation. I was just wondering, what's the main difference you've noticed between academia and working in industry?
Okay, so working in academia is fun yet frustrating. In a sense that working with the students, I would say working with the lecturers, and then it's once you go a little bit above, that becomes politically challenging and annoying, very annoying, because unfortunately some of the stuff I did so for example, setting up the lab in Queen Mary, although it was my job to do so, obviously it's not my lab, it's the lab of all the academics. So I have to make sure I talk to all the academics to make sure to make a functional lab. However, the people above always felt that the academic with the most money should have more space. But most of the time, the person with the most money has one electron microscope that can fit a tiny room. So then you have to fight the politics. I was on every meeting fighting. In industry, if my boss says here's X money to do this, I've got that independence. Boss up top, if says, oh, Chris, nah, done. There's no politics that goes back down to me. And even now, make big decisions. I'm a project manager, so I'm not saying I'm high, but there's a CEO, there's me, and I think I'm on like third or fourth. Political games there stays there. Right? In academia, it just comes down, reaches back up, catches you up and puts you in a box. And I have to say that is what made me leave, because at one point it's like, why am I pandering to that one lecturer that has one student because he has the big box and he has that one camera, where I could be making the lab a bit more functional? And it was always a fight, always a fight. Every year, oh, Christelle, this doctor's coming with 2.5 million euros. And it's like, oh, he needs space for X, Y, and Z. And it's like, oh, the instrument's coming in tomorrow. And I was like, okay, the instrument's coming in, but have you talked to the facility manager? Do we have enough gas? Do we have electricity? The politics was not fun. I do not miss that. I honestly do not miss that. I'm not an idiot. I know there's politics in industry, but it's totally different, and it's a pressure, because I do get a couple of, I think as a product manager now, I get direct CEO emails now, and I says, oh, Christelle, we need your quarterly review. You do it, but that's about the extent of it. And I don't miss that at all. And then the flexibility as well in industry. So right now, I'm a full-time product manager, but I'm co-supervising a PhD student right now at the University of Surrey, because we have a very unique instrument right now that we're testing that's giving us some really interesting results. One of my students has gone to the US to do a presentation a few weeks back. I think it's on LinkedIn, well received. So as a scientist, I'm very proud, because I'm like, oh, we've got this technology that we can now push. And now as a product manager that needs to make revenue, I'm like, oh, there's an instrument I can sell. So there's two ways to seeing that now. And he's started in January, so he's done 6 months already, and we've already got a communication that to be ready for September. Because in industry, once you have the money, you have that time, they give you the space to do the data. So he's working full-time, but he got told, summer is yours. He's paid full-time to do my PhD. So he's getting his normal salary for doing fun. So there's that flexibility, which is quite nice. So that's the difference, I would say. Cool.
So, yes, that was Black to the Future 2023. Thank you to every single speaker who has taken time out of their schedule to present and to take the time to actually work on a presentation, because I don't do them often. I had to do one recently and I was fighting for my life. So thank you all. Thank you to Professor James West for joining us all the way from the States. Thank you to our guests and to Sunday. Thank you so much for the additional guests that you have brought for us today. Thank you for the questions that you have asked, for being such a great audience. We are so happy to have had the space to just share fantastic Black research. Please go, please eat, please drink, please be merry. Yes.
Thank you for joining us for Back to the Future. There's lots of food and drink outside. Go.